All righty, here we are. Welcome, welcome, welcome. I am so excited to be here to kick off our CRAM finale. CRAM finale is day one. I'm super excited to be here. Welcome to everyone coming in, whether you've been cramming with me all spring or this is your very first time. I'm super excited to be here with you and to talk about physics for the next 5 hours. It's going to be great. So let me start by sharing my screen. We'll give everyone a minute to jump on, and then we're just going to really dive in. No time to waste. Test is tomorrow, right? But I'm super excited to be with you all. I'm super excited to hit all of the highlights today in this stream. If you don't know me, my name is Sam. I teach AP Physics C, mechanics, and we're just going to hit the highlights today, do some practice, and really just spend some time together to make sure that you're feeling good for tomorrow. So with that, I think we should get started. A reminder, especially if you've never been to one of these CRAMs before, we do practice problems throughout the whole thing, and I've got a bunch for you today. So if you want to go run and grab some paper or a pencil or a calculator, something like that, we will kind of be sprinkling in some practice problems. We're also going to do a couple of full-length free response questions in these 5 hours. So I want to give you, real kind of 15 minutes, a full free response question, so that way we can kind of get some practice in before tomorrow. So that is the plan. Super excited. And let's get rolling. So first thing, as always, we are recording this. The recording might appear on places like the 5 website, YouTube, other public spaces. So just make sure that if you don't want your name anywhere, just make sure to change your name. That's the only disclaimer there. And then I'm going to play this video. We've got an awesome social media competition going on right now. So it's just about a minute long, but I want to tell you about it because there's some awesome prizes. So let me hit play here, and hopefully you can hear it, and we'll listen to Amanda explain it.
What up, AP students? Amanda here for 5 Gold. We are literally giving away $100 to pay for your AP exam. How do you win? You just gotta post about the AP experience on social media, on TikTok, Instagram, or Twitter. Use the hashtag YesWeCram and with 5 Gold and tag us. So one person will win every single day. It is going to be a group of students who actually judge the winner. They will pick the winner. This is how they're going to choose. It has to capture the AP experience. Do they look at that post and think like, that's 100%? Is it creative? Is it funny? Does it have a really awesome song in it, or really good use of some sort of meme? Anything. You see creativity and engagement. How many likes do you have? That literally is going to help you. More likes, the more likely you are to do. And then finally, does it incorporate 5 Gold? Is it in the caption, what you're wearing, in something that you're doing? How have you incorporated 5 Gold? So this is how you can win. A couple of quick notes. Make sure you follow Think 5 Gold so we can DM you if you want. You can post as many times as you want. You can post today, tomorrow, every day, as many times during the day as you want. But you can only win once. Keep that in mind. And finally, some of our best social interns came from this contest last year. So if you're really awesome at social media and you're looking for an internship, show us what you've got. We want to hire you. So I can't wait to see your posts. See you on the flip side. Good luck in your exam.
All right.
What up, AP students?
I always do that, and it always plays it twice. Let's see. There we go. Okay, great. So speaking of social media, always we like to plug, if you have not yet followed @Think5able on all of the social media platforms, do it. We've been posting awesome tips and tricks and resources for you as we're really, this is called a cram, but we're really starting to cram in these last couple of weeks as we start taking these tests. So definitely follow @Think5able if you haven't yet. Also, speaking of, community and learning socially, as we're watching this stream, I'm here and I'm talking to you through the stream. But Kristen is also here. Kristen is our awesome AP Physics C Mechanics TA. She is here. She's ready to rock, happy to answer questions. So as you have questions, throw them in that discussion section, and we are here to answer your questions. So I'm going to be talking mostly content, and Kristen is just here as another resource for you to help as with these last minute questions that you have today. So here's the map. So we are here for 5 hours. It's so great. So in this first hour, we're going to just go over basic exam format first, just to make sure that everyone knows what's coming at them. And then we're going to talk about motion. The next hour, we're going to go from 1 to 2. We'll talk about forces. 2 to 3 is going to be the conservations, right? So we'll talk about conservation of energy, conservation of momentum. 3 to 4 is going to be rotation. And then in that last hour or so, we'll do kind of a final tips and tricks moment. These are my guidelines. This timing is going to shift a little bit as we go, just based on where those free response questions fall in and things like that. But if you need kind of a general overview of what today is going to look like, this is my plan. So first, let's just dive in. So in this first hour, we're going to talk about exam format, and then we're going to talk about motion. So as we do this, we have this awesome option here to open up polls. And so what we're going to do as we go through these CRAM sessions today is there's going to be moments where I'm going to ask you to either do a practice problem, or we'll break it up with some fun questions too. But I want to practice this poll right off the bat. So I'm going to open up a poll right now. And before we actually dive into any of this, I want to know how you're feeling. So how are you feeling right now about the test tomorrow? So take a second and think about it and give me an answer. It's okay no matter where you're at. I'm just kind of trying to get a temperature check, seeing where you are. So take another 10 seconds or so and vote. We've got so many people here today. I'm so excited. That'd be great. Yeah, and we're all over the place, which is awesome. Okay, so if you're gonna take a vote, take just another couple seconds. I think we've got a lot of people choosing an option. The votes are slowing down. Okay, great. So I just want to show you where everyone is right now, because you're not here alone, right? There's a bunch of people on the stream watching together. And so I just want to show you, this is how we're feeling right now. So some of us are super ready, confident, ready to go. Some of us are kind of like in that middle spot, right? Like feeling okay, but don't really, not great yet. And then there's some people that are like, don't know, not feeling great. It's tomorrow. But that is absolutely why you're here and why we're here for you. So hopefully the goal by the end of this, at 5 p.m. Eastern, I'm on the East Coast, so it's noon for me right now. At 5 p.m. Eastern, we're going to push that needle, at least hopefully one spot in the more positive direction. So with that, let's dive in. So first, exam format, right? So let's just get the logistics out of the way. There's 2 different types of exams that are being offered. If you're taking the exam tomorrow, if you're watching this, live on May 2nd, the paper exam tomorrow, there'll be a first section that's going to be multiple choice. It's going to be 35 questions. You'll have 45 minutes to do it. So it's a little bit over 1 minute per question, and it's going to be half of your exam score. And then if you are doing the May exams, the paper exams, the second section is going to be a free response section, right? So it's going to be 3 questions, also 45 minutes, so about 15 minutes per question, and it's half of your exam score. And I want to point out here that for both sections, you can use a calculator. So if you don't have a calculator, that's something we should find today so that you've got it ready to go for tomorrow. You can use, the 4 function is just like the add, subtract, multiply, divide, like a basic calculator. You can use a scientific or a graphing calculator. So bring that tomorrow to your test. You also will be given an equation sheet, which we're going to dive into in a couple minutes just to talk about what it looks like. And I want to point out a couple of things that maybe if you didn't look at it closely, you haven't noticed yet. If you're watching this on a replay and you're taking that digital exam in June, the only thing that's different is that second section is also a multiple choice section. So the 2 sections are, the format of them is the same. Okay, and we've got 7 units in mechanics, right? We're looking at kinematics, Newton's laws of motion, work, energy, power, systems of particles and momentum, rotation, oscillation, gravitation, right? Know that in these 5 hours, we're not going to be able to do every single piece from every single one of these units. We just don't have time. So my goal for today is to hit the highlights, hit the areas where you are going to see the most questions, and try and hit the main points for each of those areas. So I've got some stars here. Very, very frequently, especially in the free response, you're going to see a Newton's laws of motion. That's just forces, right? Work, energy, power, conservation of energy, that sort of thing, and then rotation. So we're going to make sure that we spend lots of our time today prioritizing the things that you're most likely to see the most of. You're not going to see a ton of like questions about satellites in gravitation, right? It's only 6 to 14% of the multiple choice, and similar for the free response, not very likely. So we're going to spend the most of our time here really prioritizing the heavy hitters. And like I said, I wanted to look at the equation sheet before we start. So we're going to keep coming back to this equation sheet in this 5 hours. So I want to point out, as we go through, where the formulas that I keep talking about are on the equation sheet. So I'm actually going to open it up, and I need to switch my tab. So you're going to see me for a second. And then I want to just go over it with you so that way you know what it looks like. So you're not searching it for tomorrow. If you've never seen it before, now is the time. And if you have seen it before, I want to just like make sure that you've noticed some things that are on here that are maybe not the thing that you usually use. So this equation sheet, it's got 3 sides, but it's used for both this test, the mechanics test, and the E&M test, electricity and magnetism. So I just want, for our purposes in mechanics, we're going to pull out the major things that we can use from the equation sheet for this test. And then if you're also taking E&M, the CRAM later today, we'll talk about the equation sheet in terms of the E&M test. So for the mechanics test, this first page here is just a lot of constants, right? Most of them actually for mechanics we don't care about. These are mostly for E&M, but there is a couple here. So on the right side here, we see universal gravitational constant, big G, right? And we've got the number for that. So you do not need to memorize it. It is on your formula sheet. And then I would think at this point, probably if you've been looking at this stuff, you probably know that G is 9.8, little g, right? The acceleration due to gravity is 9.8 already. But if you have a brain freeze tomorrow, that's okay. It's here for you. G is 9.8. It's written on the formula sheet. There's also some like major units that you would use, some prefixes here in case we need to convert like from centimeters to meters, for example. All of the major trig values are here. So if we needed a sine of 30, we see that it's 1/2, those sorts of things. And then there's these assumptions. These assumptions you've been really using kind of all your studying. We've just been assuming this, so you kind of don't have to worry too much about this. The only one actually that even really affects us is this first one, that the frame of reference is inertial. But we're not doing anything that's not. So everything that you've been learning has just been kind of what we've already been doing. So you don't have to worry about that. On the second page here, this is kind of the big page, right? This is the page you're going to use the most. You've got all of your formulas and what the symbols stand for. So I would say a good place for you today, you don't need to have memorized all these formulas. If you have some of them memorized, which you honestly probably do if you've been studying on stuff, that's great. But you don't need to. It's all here for you. The only thing I would say is make sure that you know what the symbols mean, right? So hopefully as you've been practicing, you know that, like, for example, F stands for force and A stands for acceleration. But if that's something where you're like, I'm still having to go back and forth, maybe spend a couple minutes reading over this a couple times today, just so that way, as you're using this equation sheet, you're not wasting valuable time trying to like decode the formula to even say what it's saying. Hopefully, by the end of the CRAM today, we can look at this equation sheet and be like, yeah, I know what all of those formulas mean. And I know like at least what topic I would use it in. So like if I look at this formula here, this sum of the torques over the moment of inertia, that's telling me like that's a rotation formula. And like even being able to do that is going to be super helpful for tomorrow. This last page here has just some math on it. So we've got some formulas for like areas and circumferences and volumes of different things. We've got a little bit of right triangle trig reminders down here. We have some of the common calculus shortcuts here, right? Like the rules that you can use. And then I wanted to point these out. I feel like everyone forgets that these exist down here, the vector products. So hopefully we've seen, and if we don't, we'll talk about it today, that some of these formulas have dots as multipliers, and some of them have crosses. They have the X's. When we see those, they function differently. And you have a cheat sheet right here. It tells you. So if it's a dot, you're going to multiply the two numbers and multiply by the cosine of the angle between them. If it's a cross product, that's the name of it, you're going to multiply the two numbers and then get the sine of the angle between them. So this is all here for you. Use it. And that is my message on the equation sheet. Okay, we're going to keep going. Let me switch back. Great. Let's get into motion. So we are going to talk in motion first about one-dimensional kinematics. So this is like day one of physics-y mechanics, talking about the different values for the different things that we can look at in motion, how they relate to each other. We'll talk about the kinematics equations. And then we're gonna look at simple harmonic motion throughout this entire CRAM in terms of the other big topics. So we're not gonna specifically talk about simple harmonic motion, but really it's just a special kind of motion that has like things in it that go with, kinematics and forces and energy and things like that. So we're just gonna kind of sprinkle it in just to keep you on your toes. So very first thing, reminder, if we're looking at position, velocity, and acceleration functions, we can relate them together. In order to go from a position function to a velocity function, we need to take a derivative. In order to go to velocity to acceleration, we need to take a derivative. If we want to go in the other direction, we integrate, right? That's calculus. Opposite of taking a derivative is integrating. So if we want to go from an acceleration to a velocity, got to integrate. Velocity to position, have to integrate. So here is your first practice problem. I feel like this is hopefully it's a warm-up. We've got a position of a particle moving along the x-axis, given by the function of time by the expression x of t. So it's a position function because we see x, right? T squared plus 8t plus 2. X is in meters, t is in seconds. And it's asking you for the velocity of the particle at t equals 2. So I'm going to open up a poll and see where we're at. Hopefully, like I said, hopefully this is something that you've seen before. If not, it might have been a minute. So if not, we're definitely going to talk about it. You may have seen this like if you've been taking it all year, like maybe you saw it in September and haven't seen it since. But let me open this up and see where we're at. Just want to remind you, because you're definitely going to see one of these on the test. So take a second and, oh yeah, we're cruising. Great. Take another 20 seconds or so to vote. We've got a bunch of votes in already. Oh my gosh, it's looking so good, y'all. Awesome, awesome, awesome. Take another 10 seconds. Also, I totally go on teacher time. So my times for these, I always say 30 seconds, then it's like 45. That's teacher time. Great. Okay. All right, all right. If you're going to vote, last chance. Okay, here we go. So overwhelmingly, not everyone, which is okay, but overwhelmingly, y'all crushed it. Take a look at that. 95% of you got it right. If you didn't, never fear. We're going to talk about it right now. Probably just made a silly mistake, but this is, most of you just like totally crushed it. So that's awesome. So how we figured this out, we have a position function, right? X of t equals t squared plus at plus 2. We need the velocity at 2 seconds. So the first question, and you're going to see me kind of structure all of the answers that I give you for questions for this whole time similarly. The first thing we want to think about is what we know and what's the relationship between what we know and what we need to find out. If you're stuck on the test at any point, that's a great first thing to be thinking about, right? What do you know and what do you need to find out? So we know the function and we know we need velocity. The relationship between a position and a velocity function, need to take the derivative. So I'm going to take the derivative of x of t to get dx dt equals, remember we bring the 2 down and subtract the exponent by 1. So it's 2t plus, and then the derivative of 8t is just 8. Derivative of 2 is 0. So 2t plus 8. And then, because we want it at 2 seconds, I'm going to plug in 2 for t and get an answer. Great work. Let's talk about kinematics. So for kinematics, there are 3 equations. They are all on your equation sheet. Great news. They're also listed right here. Remember that the kinematics equations will relate together the velocity of an object, the acceleration of the object, the time, and the position. And the goal here is basically just find the equation that doesn't have the thing that you don't know. Another probably less confusing way to say that is you need to find the equation that's got all of the numbers that you know from the problem plus the thing you're looking for. So like if we're looking at this first kinematics equation, in that equation, there are no x's. There are no positions, right? So if we would use that first equation when we don't know anything about position and we don't care about it, the problem's not asking us for it. You would do something similar with the other 2. And then one specific type of like one of these kinematics equations or kinematics problems is free fall. So remember that free fall, the rules for it is if something is in free fall motion, there's no air resistance. The only force acting on it is gravity. And then there's kind of like some tricks, right? If it's something that's dropping, so if it's like a rock dropping from a cliff or a skydiver falling from an airplane, your initial velocity in the y direction is going to be 0. If it's something being thrown upward, and I always say thrown upward because one time I said throwing up and everyone just laughed at me. So if it's a thrown upward problem at the maximum height of the throwing, the movement, the object's velocity is 0. For any of these problems, we're going to use the acceleration due to gravity. Remember, it's on your equation sheet, but it's here too. It's 9.8 meters per second squared. Quite honestly, if you wanted to use 10, you want to round that to 10 and use 10 on the test, do it. You're going to get answers that are close enough that you're going to be able to figure out what you need. And on the free response, you can use 10, totally legit. You'll not lose points. No one will get mad at you. So let's do another practice. So we've got a rocket launched straight upward. Initial velocity is 30 meters per second. Assuming that air resistance is negligible, no air resistance, so we're in free fall, right? Find the maximum height of the rocket. So take a second. I'll open up another poll here. We're getting warmed up. What do we think about this one? To find it. I have so many questions for you. I have to find this question. All right. Take a minute or so to answer that one. This one's going to take you a little longer to calculate, I know. Great. We've got some votes coming in. If you're still working, take another 20 seconds. All right, last chance if you're gonna vote. Okay, awesome. So for those that voted, again, overwhelmingly, we're right on it. So here we go. Let me show you what we got. Correct answer here is 45.9 meters. 89% of you got that right. You're great. You're going to do so well tomorrow. If you didn't, never fear. We're going to go over it right now. So the way we take a look at this is one of those throwing upward problems where at our max height, the velocity is going to be 0. So whenever we're looking at one of these kinematics equations, what I always like to do is just make a list of all of the variables that are in those equations and write down what I know. In this one, the thing that we don't know about and we don't care about is time. It doesn't tell us about time. It doesn't ask us about time. So we need to find the kinematics equation that doesn't have t in it. From there, we plug in our numbers. We solve for the position. Maximum height would be the position of the rocket, and we get 45.9 meters. Okay, so here's my sprinkle of simple harmonic motion. So first, what is it? You probably, as you're studying, did a whole unit specifically on it. The easy takeaway with simple harmonic motion, there's 3 different types of it. All of them follow the same rules, and they work kind of the same way, but you could see it 3 different ways. The first one, it's uniform circular motion. We're going to talk a lot about uniform circular motion in this CRAM later on. Second one is a mass oscillating on a spring, like you can see here. Third one is a pendulum swinging. All 3 of them create these position functions that are sine and cosine graphs. They're the waves, right? And so that's kind of like the defining feature of simple harmonic motion. We've got a general formula for it. So we're talking about simple harmonic motion in terms of motion, of like the positions and the velocities and the accelerations and things like that right now. So the general formula we've got for simple harmonic motion, it's going to be the second derivative of x with respect to t, plus a new term. Omega here is the angular frequency of the motion squared times x. And that whole thing always has to be equal to 0. This is a rule, and it's something that's not on your equation sheet. So if you've got some scratch paper and need to write it down right now, I'll leave it up for a second as you write it down. But this is something that we need to memorize because we're going to see, there's a chance you're going to see a position function that looks like this, and we need to know where that angular frequency number is so we can pull it out of the equation. If we were to solve that differential, we'll get this. So this one is on your equation sheet. We know that the position of the object is equal to the maximum position. We also call that the amplitude of the motion times the cosine, and then it's the angular frequency times t plus this I think it's a phi here, is the phase. And honestly, they never talk about it. You can ignore it. Just worry about the angular frequency times the t. And this angular frequency omega is the same thing as this angular frequency omega. Corresponds to the number of radians per second. And it's the same thing as angular velocity in uniform circular motion. We'll talk about all of that later if you're like, I don't know what she's talking about. Just write this down and you should know it because we're going to use it as we go through some questions. As far as the actual takeaway messages between the different types of values for motion in simple harmonic motion, so the position, velocity, acceleration, it works the same way. You take derivatives to go from position to velocity to acceleration. You integrate to go from acceleration to velocity to position. We also have some new things. So on top of the omega angular frequency, angular velocity, when we're talking simple harmonic motion, because it's an oscillation, it's periodic, it's does the same thing over and over and over, we've got some extra things that we can look at. First one is the period. Period here symbolized with a capital T. It's the time for one cycle or complete revolution of the motion. So basically, if we're doing it in terms of the position function, it's one wavelength, right? It's an up and it's a down, and then when you're about to go up again, that's the end. If we're talking frequency, the frequency, we symbolize it with a lowercase f, and it's just the opposite, it's the inverse of the period. So if the period is the time to complete one cycle, frequency is the number of cycles per second. We measure it in hertz, like the light bulbs. You probably have a light bulb that has hertz on it. It's the same idea. And they're inverses of each other. So if we're looking, t is the period over here, it's equal to 1 over the frequency. It's also more generally equal to 2 pi over the angular frequency. And that's something, like I said, we'll talk about it more later, but I put it here because it does have to do with motion. So I thought we would just introduce it here and then revisit as we go through the CRAM session. So here is another practice problem. So this is going to use that general formula of the simple harmonic motion. So we've got an equation. We've got the second derivative of x with respect to t is equal to negative 9x. X is the, I can't speak. X is the displacement, t is the time. It's asking for the period. So we're going to want to combine, go backwards for a second. We need to recognize how this formula is the same as the one in the problem. And then we're going to want to relate it to the period using this formula. So take a second. I'll open up a poll, see what we can get for this. All right, when you're ready, take a vote. I'll also note that anytime I use one of the old, there's a 2012 public exam and there's a 1998 public exam that I pull a lot of multiple choice questions from, but it's always A through E, and my poll only gives me 4 options, so there's always like a random letter missing. But I promise there's no like reason, like there's no method to my madness. I just take one out. But you know that one can't be correct, I guess is the only thing. So in this time, you know it's not A. All right, we've got a lot of votes in. If you're going to vote, take another, oh, I don't know, 20 seconds. Yeah, it's looking great, y'all. Great. Man, those correct numbers are just flying in. So great. Okay. All right. Last chance. Okay, here we go. Overwhelmingly, again, I do think that percent yes is getting a little bit lower, but you're still at 82, which is so good. Awesome. So let's go over it for those that didn't get D as the correct answer. So the first thing here is that we know that we recognize that we've got this second derivative of x, and then we've got x in the same equation. When we see that, we're immediately like, okay, that's the general form of simple harmonic motion. So I need to relate it to this guy. And I'm going to just rearrange it so that way it looks like the general form. So that way I can pull out the angular frequency. So all I did is I moved that 9x over using algebra. And then from there, I recognized that in order to figure out the period, I need the angular frequency. In order to get the angular frequency, look at this general formula. We know that this 9 here represents the angular frequency squared. So I just take the square root, I get 3, and then I plug it into my period equation and get D as my answer. Cool. So a couple of more specific period equations, just to run through quickly so that when you see it on your equation sheet, you know what it is. In order to find the period of a mass on a spring, we can use this equation. The two things that affect the period of a mass on a spring are the mass of the mass on the spring and then the spring constant of the spring. So that hopefully you're thinking about it and you're like, okay, that makes kind of sense, right? Because if it's a mass on a spring, we have to worry about the mass, we have to worry about the spring. So that's our formula to find the period of a mass on a spring. And then the other simple harmonic motion is pendulums. To find the period of a pendulum, we'll worry about two things. We worry about the length of the string. So like if it's a pendulum, it's swinging back and forth. We worry about the length of the string, and we worry about the acceleration due to gravity. You're going to see, there's a chance you're going to see a question that's like, we take the pendulum to Mars or to some other planet where the G is different, how does it affect the period? It will affect the period of a pendulum right here. And the reason is because the force or the torque that's causing it to swing is the weight of the bob at the end, which, if it's the weight, then G affects it. But if we take this, an oscillator to Mars and the oscillator's a mass on the spring, we don't care about G for that, right? We just care about the mass and the spring constant. So this formula is here for you as well when we're thinking about the period of a pendulum. I put this in here, the small angle approximation. Every once in a while it pops up, so just so that way you've seen it before. All it says is that if it's a pendulum, it's a simple pendulum, which is just like the string and then the bob at the end. They all have the same period regardless of the initial angle. So when we're doing the math, we can take the sine of the angle if we're trying to derive it and just make it equal to the angle. So this derivation, technically it's something that you need to know how to do. I think as long as at this, like the test is tomorrow, right? So let's be realistic. As long as we have heard of the small angle approximation before, if you've never heard of it, now you've heard of it. And all it means is that the angle for the pendulum, it doesn't matter. Okay, two-dimensional kinematics. This is where it gets real. So we are going to talk about what happens now when we add in that second dimension. And we'll talk about things like vector components and reference frames and projectile motion. So vectors and vector components. Hopefully this is something that this kind of pops up throughout the whole term, right? As you're going through mechanics. And so this is something that you've probably seen before. But I want to just be clear. I want to just make sure that in case you were ever confused with how this works, we see it today. Whenever we're looking at more than one dimension, and by that I mean like the x-axis and the y-axis and not usually the z-axis, but it would be 1, 2. Z is like in and out of the page. Whenever we're looking at more than one direction, the directions are independent of each other. So what we have to do is we have to figure out what's going on in the x direction, figure out what's going on in the y direction, and at the very end, we combine them together. And the easiest way to do that, at least for me, is to do this graphic vector addition, which is just a fancy name for make a triangle and figure out what the hypotenuse is. So the hypotenuse, we call it the resultant, right? That's the physics name for it. And all we're going to do is we're going to use right triangle trig to figure it out. So we would figure out the length of that side, probably using a squared plus b squared equals c squared. And then we would find the angle using right triangle trig. I also have this in here. Probably you won't see it, but in case you see anything that's got like an eye with a funny looking hat over it, it's actually called a hat, or a J with a funny looking hat over it. The I is the X component, the J is the Y component. It's called unit vector notation. I would say if you've never seen it before, now you've seen it, and that's good enough. For a projectile motion, here we go. What is it? So it's when objects are launched in the air, but now we're not just like dropping or throwing upward, we're going in more than one direction. And so there's two real major types. The first one is horizontal projectiles. So that's something that's launched, you guessed it, horizontally from a height. And then there's launched at an angle. And that can also be from an initial height, or that sometimes is from the ground. And usually you're either given the angle of the launch, most likely, or you could figure it out depending on what else you're given. And the nice thing about projectile motion is that it's kind of the same as one-dimensional free fall motion, just with like a little bit of an extra twist. Dropping problems in one dimension are just like horizontal launch problems in 2 dimensions. And the reason is because in the y direction, that initial velocity for both of them is 0, and your acceleration in the y direction is negative 9.8 meters per second squared. That's the same. The only difference is that when we launch horizontally, it's going in the x direction too, right? But there's no forces happening in the x direction, so that velocity in the x direction is constant, and we'll talk about that more in a second. Thrown upward is just like, or launched at an angle is just like thrown upward with a twist, because in launched at an angle problems and in thrown upward problems, your velocity at the max height is 0. And your object starts with some initial velocity in the y direction. So this is a great picture. Oh, Kristen, I still have this here. Kristen suggested this picture to me when we used it earlier in the spring. This is a nice little way to kind of unpack what's going on with the velocities if we're looking at launch at an angle, which is like the most complicated one, right? The velocity in the x direction we can see is the same the whole time. There's no forces acting in the x direction, so there's no change in velocity, right? That x direction is the same. And then in the y direction, we start with some initial velocity. At the top of the motion at max height, the velocity is 0. And then we can see the velocity changing on the way down. And you can see how there's like the x component and the y component, and then the resultant velocity here, and then here, and then, it follows the path of the parabola. Okay. So here's kind of a breakdown. If you have a projectile motion problem, this is usually how I like to set up my chart just to figure out what's going on. First thing, always draw a picture. You're going to hear me say that for the next 4 hours and 20 minutes. Draw a picture, draw a picture, draw a picture. After you've drawn a picture, I always like to set up a separate column for the x direction and for the y direction. That just reminds me that we have to keep them separate from each other, and those numbers have to stay kind of on their own side. In order to find the initial velocity in the x direction and in the y direction, what you're going to do is you're going to take the initial velocity, the initial launch velocity, and the angle, and find the x and y components of it. From there, your velocity in the x direction stays the same. If you're asked to find the range, you're looking for x. That's the name that we give to the distance it goes in the x direction. It's called the range. And your acceleration in the x direction is 0. In the y direction, you'll find your y component of your initial velocity, and then it depends on what you're looking for. If you're at max height, then the velocity is 0. You could solve for your max height by solving for y. Your acceleration for this is always going to be negative 9.8 meters per second squared because you're in free fall. And then the biggest takeaway with this is that in order to connect the x direction in the y and the y direction, in order to kind of like get enough info to bounce between them, the first thing you're typically going to want to look for is time, because the object is going to be moving for the same amount of time in the x direction and in the y direction before it hits the ground or whatever it's hitting, right? So time is your connector between the two dimensions, and it's going to be the same in both columns. So when you look for time, you can actually fill it in for both of these columns. So that's kind of like how I set up projectile motion stuff. So here's another question. We've got an archer shoots an arrow horizontally from a height of 3 meters with a velocity of v0. Arrow hits the target flat on the ground. The arrow hits a target that's flat on the ground, and we're looking for the position of the target on the ground. So we're looking for the range. So take a second and see if you can answer that one. I will open up a poll. Make sure y'all are still there, ready to go. There we go. Take a minute. All right, we've got some votes coming in. All right, if you're going to vote, take another 10 seconds or so. So I know this one takes a couple more. As we get more complicated, it takes longer, right? I totally get that. All right, last chance. Okay, here we go. So this one we're a little bit more split, which is good. That's why you're here, right? We're learning. So let me show you what we've got. So the correct answer here is going to be B, and let's talk about why. So, like I said, first thing I like to do is just draw my picture and set up my chart. So I've got, we know from the problem that the velocity in the x direction is v naught because it shoots the arrow, the archer is shooting the arrow horizontally, right? So that x direction is where the velocity is going to be, and it's equal to v naught. We know it starts at 0 just because that's how that's where it starts. We know the acceleration is 0 in the x direction, and we're looking for that range, right? We're looking for x. In the y direction, as a rule, if we're launching horizontally, then the initial velocity in the y direction is 0. There's no component, if we can think about it this way, there's no component of that initial velocity that's pointing in the y direction if we're launching horizontally. So our velocity is 0. I set up so that my initial height was 3, my final height was 0, my acceleration is negative 9.8. From there, I used my y side first and used the kinematics equations to solve for t. And then from there, I plugged in t and realized that I could use this kinematics equation and solve for an expression that has v naught in it. I think sometimes it's hard to be like, looking at it and you're like, okay, well, I have it in terms of v naught. That's weird. How do I figure that out? And sometimes it just takes some kind of just like messing around, playing around with a formula to get something in terms of v naught. You see in the answers that your goal is to have something in terms of v naught. So you know you're going to need to end at like the last thing you're going to do is use the x values, because we know that v naught is only in the x direction. So as I was looking at that, I was like, okay, well, I guess if I'm going to end with my x values, but there's not enough info here yet, I need my time, I'll start with y, get my time, and then move over. Okay, and I think this is the last question for motion. So here we go. Which of the following graphs, or at least for projectile motion, which of the following graphs represent the vertical component of the velocity of an object launched from the ground at an angle theta above the horizontal? So we're looking for the vertical component of the velocity, and it's launched at an angle. So let me open up a poll and see what we can do here. Frequently, tomorrow, you'll probably see a graph or two that looks like this, or have to make it, right? So it's important to be able to not only use the numbers, but also be able to read the graphs. Great, we've got lots of votes in. Take another couple seconds if you're voting. All right. Okay, so let's take a look at this. Overwhelmingly, we picked B. Forgot to mark the correct answer, so we'll just look at it here. Correct answer is B. That's great. So if we take a look at it, if we're launching from an angle, from the ground, at an angle, theta, above the horizontal, we know that as I'm kind of looking at this, what I want to do is I want to look at the major points in that motion, think about them, and be like, okay, what does that look like on a graph? So we're launching from the ground at an angle theta. So it's doing that, parabola looking motion. And it's going to start, if we're launching from the ground upward, it's going to start with a positive velocity, right? It's going up. So right away, I actually have my answer, right? Because this one starts with a negative velocity, A here. C starts with a velocity of 0. And D starts with a negative velocity. So right away, my answer is B. But if we want to kind of go through the rest of it, just to confirm, we can. We know that as it's going through the motion, it's in free fall. So it's got that negative acceleration. So we know that on a velocity time graph, the acceleration is the slope, right, or the derivative. So we need to also look for something that's got a negative slope. Check for B, right? Check mark. It does. We know that at some point it's going to be at its max height, and in the y direction, it's going to stop. So it has to cross the axis because the velocity has to be 0 for a moment. And then it's going to start falling with that negative velocity down here, right? So that's how we kind of unpack the graph to match the motion. So if we go back to the equation sheet, I'm going to switch my screen again. I wanted to just, at the end of every big chunk, take a second and just look at the equation sheet and talk about what we did in terms of the equation sheet. So let me switch it over again. I'll see me. I'm still here. I know you can hear me, but you can also see me. That would be the slides again. There we go. So if we take a look at it in terms of the equation sheet, I wanted to just show you, we looked at these first 3 equations right here. In this first hour, we looked at these first 3. We also looked, scrolling down, trying to find, we looked over here, this period equation right here for simple harmonic motion, and then these 2 period equations for pendulums and for springs, mass on a spring. And I think in this first hour, that's what we hit. My goal is to hit a vast majority of these equations at some point today. And we're off to a really good start because we've already hit 1, 2, 3, 4, 5, 6. So we'll just keep rolling. Let me switch back. That's great. You see me dancing. This is behind the scenes. Great. So from here, we're going to take a 5-minute break, and we're actually a little bit ahead of time, which is great. So at the end of every big chunk, we're going to take a 5-minute stretch break. I definitely need to go get some water. If you haven't yet stood up in this hour, take a minute to stand up, take a stretch, get a snack, and then we will come back in about 5 minutes. So it is 12:50. It'll be 12:53 and on the East Coast when I'm done talking. So we will come back at 12:58. So go get a snack, and I'll see you at 58, I guess, no matter what number comes in the hour. We'll be back at 58. All righty, here we are. Alrighty, folks, and we are back. Hopefully you went up and got some water, took a stretch break. We are going to keep cruising. So just as a checkpoint for where we are right now, we just finished our first hour, or we're right about there, talking about the format of the exam in motion. We are headed into forces. I will warn you that at the end of forces, we are going to do our first full-length free response. So it will be a primarily forces free response, and you'll have 15 minutes to do it. I'm going to time it, and then we'll go over the rubric to score it together. So that's where we're headed. But in order to get there, we actually have to talk about forces first. So that's what we're going to do. So the first section of forces is just talking about Newton's laws. So we'll talk about Newton's first, second, and third law. We'll talk about the concept of equilibrium. And then we are also going to talk about simple harmonic motion in terms of forces. So here we go. First thing, Newton's first and second law. Really, all of it comes down to Newton's second law. Newton's first law is just a special case of Newton's second law, so you can kind of just like not even worry about it, because as long as you know how to use Newton's second law, Newton's first law is kind of just like already there. Newton's second law states that the acceleration of an object, this is like the fancy physics, right, is directly proportional to the net force and inversely proportional to the mass. All of that means is the force is equal to the mass of the system times the acceleration of the system. It looks like this on your equation sheet. They write it, they have A there first, right? A is equal to the net force over the mass, but that's F equals ma, just rearranged. And remember that when you're doing this with the forces, we have to keep the forces in the x direction separate from the forces in the y direction. So we do all of the force stuff in each direction separately, and then just combine whatever you're looking for at the end. I will talk about Newton's first law in just like very briefly. All it says is if the sum of the forces is 0, there's no acceleration. The formula, like I said, the formula says that, right? If our net force is 0, A has to be 0. And the way that they kind of like expand on it is that if the object is at rest, it's going to remain at rest. Object in motion will remain in motion with a constant velocity, not changing its velocity, not accelerating, right? Okay. There's also this idea of equilibrium. Equilibrium, sometimes they'll explicitly reference it, but really it's just kind of like the name we give to what's going on in a situation. And I like to just make sure to explicitly talk about it, just because when I see equilibrium, in that word equilibrium, I see equal, and it helps me to remember what I'm looking for. Equilibrium happens when the net force of an object is 0, or the net forces on the object is 0. So what we were just talking about in Newton's first law, if it's in equilibrium, it's not accelerating by definition. And there's two different types. There's static equilibrium, which means that the object is at rest. So this chandelier is an example. We'll do another example with a sign in a minute. There's also dynamic equilibrium, which is kind of one that you have to like, I always have to sit and think about it for a second, because you're like, it's moving. Why are, maybe there's forces acting on it. For all of these equilibriums, forces are acting on the objects, right? We're on, for all of these examples, we're on Earth. Gravity is acting. There's tension forces in the chandelier. There's frictional forces, but the key here is that the forces are canceling each other out, and the net force is 0. In dynamic equilibrium, it's moving at a constant velocity. The velocity does not equal 0. It's moving, but it's at a constant velocity, so it's not changing its velocity. So here's an example of static equilibrium. So frequently we'll see this, especially on like a free response type of question. So I wanted to just go over it. We've got a 2-kilogram sign hanging from the awning of Joe's Pizza. Joe's Pizza is not real. I made it up. Just wanted to have a sign that's hanging. And we're asked to calculate the tension in each of the ropes that hold up the sign. So we're going to go through this. I'm not going to spend a ton of time on the actual algebra piece, hoping that that part's okay. I want to really just focus on the physics parts for all of these force problems. So whenever we have a force problem, we're going to do the same thing that we've always done, which is just write down what you know and what you're looking for. But a lot of times in forces, that's going to be in terms of a free body diagram, an FBD. That's how we abbreviate it. So when we draw a free body diagram, remember that we start with the object and like a dot at the center of mass, and all of the arrows point outward, and the vector arrows, right? And those symbolize the different forces. The longer they are, the bigger the force, and they point in the direction that it's going. So I've got my free body diagram here. If we're looking at the sign on Joe's Pizza, the force of gravity is acting on that sign pointing down, and then each of those ropes are providing a tension force pulling up at different angles. Note that I also drew the components of those forces here. I will point out, and I'll say this again at the end, if you're doing a free response question and they ask for a free body diagram, you don't want to draw components on that one, but you can always draw a second one and put components on it, kind of just like as a side, like you have like the official free body diagram, and then you have your free body diagram, like cheat with the components and whatever else you need on it. So we've got our free body diagram set up here. We've got our angles. Our next step always for these force problems is to write the sum of forces in each direction. So I wrote my sum of forces in the x direction using my x components, sum of forces in the y direction using my y components. Because I know the sign is not moving, it's in static equilibrium. So I know that each of the directions, sum of the forces has to be 0. And then from here, like I said, this part I'm not actually going to go super deep into because it's algebra, but we're just going to do some math. So we've got 0 equals each of these equations. And then what I did is I used a system of equations to figure out my answers to those problems. Newton's third law. So Newton's third law says that forces during an interaction are equal in magnitude and opposite in direction. And this is a conceptual. Really, like they're really just going to ask you about this almost definitely conceptually. Just remembering that for the name we give it is action reaction, right? So for every action, there's a reaction. As this person is pushing on this wall, the wall is also exerting an equal and opposite force on the hands of the person. And like I said, the name that we give to that is an action-reaction pair. So here's another practice problem. We've got a motorboat speeding through a lake when suddenly a bug flies into the windshield and goes splat. What statement is true about the forces involved? So I'll give you a second to read it. I'm going to open up another poll question here, and then we will go from there. Let me find it. Great, so take a second and read it. This is a Newton's third law question. Great, we've got a lot of answers rolling in quickly. That's a good sign. Okay, take another 5 seconds or so. If you're voting, dude, y'all, wait till I show you what happened. We're so close. Okay, I think we've got almost everyone. Great, so I'm going to show you overwhelmingly. Got it right. Amazing, amazing, amazing. You're going to do so well. So answer C here. Let's talk about it for a second. So if we read this, this is something that's very not intuitive, right? Like your brain kind of explodes when you think about this, but it is a Newton's third law question. The force of the bug on the windshield, by definition, because of Newton's third law, has to be the same as the force of the windshield on the bug. Those forces are equal and opposite. They have to be the same, right? The thing that's different is the acceleration that happens because of that force. So the bug goes splat because the acceleration is so much bigger. But the forces themselves are always going to be the same. So anytime you see this about like what are the forces involved in this interaction? If it's two things and they're exerting force on each other, that force is the same. Done. Over. Always true. If you see a question like that. Okay, so I know there's lots of requests about simple harmonic motion. I'm looking in the discussion. So I'm going to definitely make sure that we talk about the simple harmonic motion, as we go throughout this CRAM. So let's talk about force in simple harmonic motion. So really the kind of the extra layer that we give to forces when we bring in simple harmonic motion is this idea of a restoring force. So the best example of this is going to be simple harmonic motion when we look at a mass spring oscillator, a mass on a spring. The spring is exerting something called a restoring force, which is basically the thing that's making it oscillate, right? It's going back and forth. We can look at this image here. And it's basically continually pulling it back to the equilibrium position. But because it's in motion, it's going to stay in motion, right? Assuming there's no friction. And so that oscillation is going to continue to occur. We have a formula to help us know about the restoring force for a mass on a spring. And it's this one. It's called Hooke's law. It's the force is equal to negative K. Remember that K is the spring constant. Its unit is newtons per meter. And it's just a number. It's a constant. And all it tells us about is how stretchy the spring is. So if we think about different springs, so the examples that I always use with my class is if we think about like a mattress spring or like a really big trampoline spring, those are really going to be hard to stretch out. It's going to take a lot of force to stretch that spring 1 meter. That's going to have a big spring constant. If we think about something like a slinky, so I'm old, so slinkies are toys. Maybe you don't know what they are anymore, but it's like a toy that was a spring that was really, really loose, and you like play with it, and it would like go down the stairs, and there was like a song and stuff. Anyway, you could Google it. You're on your computer, right? That slinky would have a small spring constant because it was really easy to stretch. It did not take a lot of force to stretch it 1 meter. Our unit for spring constant is newtons per meter. So basically it's saying how many newtons of force does it take to stretch the spring 1 meter? X in this formula, delta X, X is the distance the spring is stretched or compressed. So if we took a look at this picture, when we started this oscillation going, we see that we can pull the spring away from the equilibrium position, and that distance from zero, if zero is the equilibrium position, that distance from zero, that's your X. So it's the distance away from equilibrium that the spring is stretched or compressed. When we see this talking about forces, talking about simple harmonic motion, Newton's second law is still your go-to. Even if we're talking about simple harmonic motion, as soon as we bring forces in, you're probably going to use Newton's second law. It's just kind of like your default for anything force related. Okay, let's talk about friction. So far we talked about equilibrium. We talked about what happens when things are moving either at rest or moving at a constant velocity. Let's talk about friction now, because friction kind of adds that extra layer. And I feel like friction's you're like, oh, there's no friction? This is easy, I can do it. And then you see friction and you're like, shoot. So let's just talk about it and do a little bit of practice. So first, what is it? How do we do it, right? So friction is the interaction between the object and its surroundings. So we all know it, we have friction in our lives all the time. You roll a ball across the floor, it's going to stop because of friction. We all probably, I guess I shouldn't assume, but we all probably have encountered the word friction before and definitely experience it because it's everywhere, right? There's two specific types of friction that we look at in this class. We talk about static friction. We talk about kinetic friction. So static friction is the friction that objects have when they're not moving. Kinetic, we think kinetic is like moving, right? Kinetic friction happens when objects move. And both of them depend on two things. They depend on something called the coefficient of friction. That's mu here. And mu the coefficient of friction is a constant for a surface, and it tells us how slippery it is. So something like ice would have a smaller coefficient of friction than something like sandpaper or carpet. And then it also depends on the normal force. The normal force is, remember, is the force exerted by surfaces, right? You probably, if we're talking forces, that's like a pretty first thing to learn. The way we calculate friction, it's on your equation sheet. Yay, check another one off your list. The force of friction is less than or equal to mu times the normal force. And this formula, I feel like, is always really, really intimidating because there's like absolute value bars and there's a less than or equal to alligator, and there's just like a lot of extra stuff in it, right? So I wanted to just unpack it for you. The reason it's written like that is because it depends. It's a little different depending if it's static or kinetic, but it shouldn't be intimidating. So if we unpack it, if we're looking at static, I want red because it's like stopped, you know. Static friction, we would use the formula with that less than or equal to alligator, because static friction is going to increase to prevent the object from moving up into a point where it's like at its maximum, and then from there the object starts to move. So in order to calculate the static friction, we would do a less than or equal to the coefficient times the normal force. If you see something like an object is about to slip, then this less than or equal becomes an equal sign because we're at like max static friction before it starts to move. Kinetic friction is easier. It's always an equal sign. And so the kinetic friction is just equal to the coefficient times the normal force. Okay, let's do a practice. So we've got a lot of words here, so let me help you unpack them. Block right here, pulled across a rough surface. We see that word rough, and we see, okay, rough means friction. As shown above, we know the coefficient of friction. We know that the force F pulls is exerted from an angle, I think it's a phi, shown. Which of the following is an expression for the magnitude of the frictional force of the block if it's moving at a constant speed? So this is going to be something we'll talk about more later, but notice that you have to read this whole thing before you see moving at constant speed. And moving at constant speed is going to be really important as you're answering this question. So just as we're looking at multiple choice, make sure we read the whole thing, pull out all of the information we need before we start working on it, because constant speed is going to be important as you're solving this. So let me open up another poll. I'll give you a minute or so to work on it, and then we'll go from there. Take another 30 seconds or so. All right, if you're going to vote, last chance. Okay, we're actually super split on this one, so it's actually really good. Let's take a look. Correct answer here is B. So for those that picked B, good work. But we are very split. So let's take a look and just see what we've got here. So first thing I did when I saw this problem, I was like, oh, there's a lot of forces involved. Let me draw a free body diagram. So that's what I did first. So we know that we've got that force being pulled at some angle going on. We also know that there's friction. And if the force is pulling, if the x component of the force is pulling to the right, the friction is going to act opposite it. So it's going to be pointing to the left. We know the block is on Earth, or I guess we assume the block is on Earth. So there's some force of gravity and then the normal force of the surface as well. From there, I was going to go ahead and write my sum of forces in each dimension. So let's unpack this a little bit. In the x direction, I need to take my components of that applied force, right? Take my components of that applied force. So it's F cosine of the angle, and then minus the force of friction. And then in the y direction, we have to make sure that we take the y component of that applied force, the normal force, and then we subtract out the force of gravity. So from here, we have to kind of just like figure out what's going on in the problem. So in this case, we have to think about, is the block in equilibrium or is it accelerating? We know the block is in equilibrium because it's moving at a constant velocity. So the sum of the forces in each direction has to be 0. Well, some of the forces in the x direction has to be 0. And then we know that the block is sliding horizontally. So it's in the y direction, it's not moving up or down. So the sum of forces in the y direction has to be 0. From here, we're just going to plug in what we know and try and get an answer. In this case, it's asking us for the force of friction, the magnitude of the frictional force on the block. So I'm looking for F sub F, right? And so I'm going to use my x to figure it out. I know that in the x direction, my sum of my forces is 0. And then all I did is I solved for the force of friction and got F cosine of the angle. So that's it for that one. Hopefully, if we get to a point as you're working on a multiple choice problem where you're like 2 or 3 minutes in, you're like, I still am not any closer to an answer. This would be an example, I feel like, of one of those times where maybe you like went on a weird tangent, weird place in maybe the y direction, or kind of went on a weird path in a different direction. Would be a moment where you would step back and pause and be like, okay, it's a multiple choice. I know it's supposed to take me like a minute. What am I doing wrong? And hopefully we would see that we would move to the x direction and solve in that way. Okay, let's talk about drag force, just the highlights. This is something that you might see on the test, but it's always very hit or miss. So I do want to show you, but we won't spend a ton of time unpacking because it's mostly here a lot of calculus, and the physics itself isn't always, there might not always a ton of physics. Usually it's like a little bit of physics and a lot of math. So what is drag force? Drag force is basically like friction through the air or through a fluid of any sort, right? So objects that are moving through a fluid like air will encounter the air molecules or the water molecules or whatever it is and experience resistive force. We note drag force usually with a capital R or an F sub D. And just like friction, it's going to act opposite the direction of the motion. There's 2 possible formulas for it. The test will give it to you, whichever one you're going to use, but I wanted you to at least see them, especially the second one because it looks scary, even though it's actually very not. The first one here, the drag force is equal to negative. B will be a constant, and then V is the velocity. So that's a pretty straightforward one, right? This is one formula for drag force. The other one is, like I said, a little bit more complicated. But not, or it looks scary, but it's not as scary as it looks because a lot of it's constants. So drag force could be written as 1/2 the drag coefficient, which would be a constant, the density of the fluid, which would be a constant, the cross-sectional area perpendicular to the motion, which would be the same for the whole thing, and then the velocity squared. So you could see either, but if you see the second one, a lot of those things are just going to be constant the whole time. So you can just kind of leave them there. You don't have to worry too much about them, or they'll give you a number and you can just plug it in. Relatedly, we'll talk about terminal velocity. So terminal velocity, the definition of it, it's the maximum velocity of an object that's falling. The object will have reached dynamic equilibrium. So remember what that means is the object is falling at a constant velocity. So it's moving, but it's moving at a constant velocity, and the forces are canceling each other out. They're equal. The net force is zero. Best example is like a skydiver. As a skydiver is falling, the force of gravity is pulling them down, and it's going to be equal and opposite to the drag force once that skydiver reaches terminal velocity. On a graph, we see that velocity as the skydiver is falling is going to increase, and then eventually level off. And then once we've leveled off, that's what terminal velocity looks like on a graph. Okay, so let's talk about some special cases here. So there's a couple of different special cases that go with forces. We'll look at pulleys and Atwood's machines. I feel like those pop up almost every year. You'll probably see one. We'll talk about ramps, and then we'll talk very briefly about universal gravitation. I didn't really know where to put universal gravitation. I wanted to just talk about it at least a little, so I threw it in here. That's going to be like that Unit 7 last part, which again is not super... you're not going to see a lot of it on the test, but I wanted to at least show it to you so you're not going to, you've seen the formula and you know how to use it. Okay, let's talk about Atwood's machines. So Atwood's machines are the machines that look like this, where you've got two masses and they're attached to a string, and the string is wrapped around a pulley. And if it's an Atwood's machine that straight forces, not having to worry about rotation of any sort, then the pulleys are going to be massless and frictionless. What that means is they don't have any effect on the motions, what you're looking for. This is definitely not always true. Sometimes they give you a massive pulley, and you have to start talking about rotational inertia and those rotation ideas that we'll get to in a little bit. But sometimes if the test is really trying to test out your forces knowledge and less so your rotation knowledge, then they'll give you a pulley that's massless and frictionless. And then that you don't have to worry about the pulley at all. You just have to worry about the blocks. Another kind of good rule when we're looking at Atwood's machines thing to remember is that the tension in the string is going to be the same throughout the whole time. So that allows you to be creative around whether you want to treat each mass separately and look at the forces in each mass separately, or you want to treat the system as a whole thing together and then just look at the external forces there. I'll talk about the difference in a minute. A couple of tips when we see Atwood's machines, adopt a sign convention. So think about what direction do you want it to be positive, and then if you see an Atwood's machine, probably at some point you're going to use Newton's second law. That's just you see it, you're like, okay, this is a forces question, at least in some way. So we're going to walk through an example here. I'm not going to ask you to do this one yourselves for a poll question. I just wanted to talk through it because I think sometimes with these, there's a couple of tips and tricks and strategies that I wanted to make sure we talked about. So we've got two masses hung at rest by a massless cord around a massless frictionless pulley. So again, all that's saying is the only thing we care about are the forces acting on the masses themselves. We know that mass 1 is 5 kilograms, mass 2 is 8 kilograms, and we want to find the resulting acceleration of mass 1. So here's what we do. First thing, draw a picture and decide what direction is positive. So here's my picture. I always make positive going to the right when I can. I don't know why. That's just my brain, how my brain works. I also, in this case, it works out because I see that my mass 2 is 8 versus 5 for mass 1. So it's going to move in that direction, right? It's going to move in the direction that my arrow is pointing. So I like to make that positive, so that way it's moving in a positive direction. From there, I'm going to draw free body diagrams for each mass. So this is always a good way to start any sort of Atwood's problem that you see. Sometimes they'll also be kind of looking like this, but on a table or something. This is still a really good strategy. So figure out what direction is positive and then draw a free body diagram for each mass that's in the situation. For this situation specifically, there's two forces acting on each of the masses. We know that weight is going to be bigger for the 8 kilograms versus 5 kilograms. We also know that the tension in the string is the same. So that Ft is going to be the same for both masses. From here, the next thing that I would do is write net force expressions. So this is not something now where we have to worry about X and Y. We're just going to worry about it kind of all going in the same direction. Sometimes I think about it like almost like stretched out and moving, all moving in the same direction. I also want to note the way that I do it here, I combine my system. And so I only look at the weights as my external forces. I combine it so that I'm looking at the mass 1 and mass 2 together. If I do that, tension here becomes an internal force and we don't have to worry about it. That's something you could do. If you're freaked out by that or don't like that, you can also treat each block separately and write separate net force equations for the 5 kilogram and for the 8 kilogram, and you would have tension included in those. You could do that too. The math will still work out either way. The tension forces will eventually cancel out and you'll get to the same final product. I find it simpler to combine them and just keep the weights as the external forces acting. The only trick when you do that is we have to make sure we take the mass of the whole system, not just of one of the masses. So let me show you what I mean. I wrote my net force equation. I said that the force of the weight for the 8 kilogram block minus the force of weight for the 5 kilogram block is going to be equal to my net force. Great. And then all I did is I plugged in for weight mg for each of them, right? And then simplified and got 3g. From there, I know that I'm looking for my acceleration, so I know that I need to use Newton's second law. I've got a net force expression. It's not in equilibrium. It is accelerating, so I can use Newton's second law to find that acceleration. The only trick, because I treated the whole system together as one thing, my mass for mass times acceleration, my mass has to be the mass of the whole thing, which is why I have 8 plus 5 here to get 13 and then to solve for A. Okay, so that's kind of the general idea with Atwood's machines. Draw free body diagrams for each of the blocks, decide if you want to treat them together or separate, and write the net force expressions from there, and then use Newton's second law as you need to figure out what they're looking for. Great. So then the next special case I want to talk about is ramps. So ramps for me are the trickiest ones. I don't know why. Sometimes my spatial reasoning is not great. And so I have to just like really, really, really kind of unpack and draw these a couple of times just to make sure I'm not missing anything. And there's a couple of tips and tricks when we see something on a ramp. So the biggest kind of thing to remember when we're looking at ramps is that when we're looking at an object on a ramp, the normal force of the ramp, like the support force of the ramp on the object, is not equal to gravity. If we're on a flat surface, we know that the normal force and gravity are probably going to be equal. If we're on a ramp, that is not true. They are not equal to each other. And so we have to kind of rearrange our axes to account for this. So I've got Alexis here. She's doing a head tilt, so that way you can see kind of how, what I'm talking about. She's tilting in the correct direction. And this is what I encourage you to do. So instead of having your normal up and down axis, up like the Y being up and down, X being left and right, do a head tilt and make the X axis of your setup parallel to the surface of the ramp. So whether you're like, I always like when I teach this picture, you all like sitting for the test, looking at your paper, and then your head is tilting. Just like I feel like with the right hand rule, everyone's like in the air waving their hands like they just don't care. But anyway, you're gonna do the head tilt, right? And you're gonna do that to draw that pseudo axis. So that way, when you're working on the components of things, most of your forces are going to be on one of the two axes, and you only have to take components for gravity. You can do it the other way, but you're going to have to take a lot more force components, and it's going to be a lot harder. So if we do that, normal force will be now on the y-axis. If you've got any friction, it should be on the x-axis, et cetera, et cetera. The only thing that's not is gravity. And then there's this also, this nice little geometry trick where if we know the angle of the ramp here, that's going to be equal to the angle between this y-axis and the gravity vector for this problem. Because of geometry. And geometry is awesome, and we could go through it, but the test is tomorrow, and I feel like we need to prioritize. So just trust me, this angle is equal to the angle of the ramp. Okay, so again, I'm not going to have you do this one yet. I'm going to just talk through this as an example, just to kind of show you how it could happen. So we've got a block placed on a 45-degree incline as seen below. The object accelerates at 2 meters per second squared. We need to find the coefficient of kinetic friction of the ramp. So here we go. First thing I'm going to do is draw it out, and I'm going to do my head tilt. So I set my axis, my x-axis parallel to the ramp, my y-axis perpendicular, and then I draw out my forces. So I've got a normal force pointing in the upward y-axis. I've got my force of friction acting in that x-axis, and then I've got my gravity and my gravity components. From there, I write my net force expressions in the x direction and in the y direction, noticing that I take the components of gravity as I do so. From there, I know some other info to help us solve the problem. So I'm going to first kind of just like go through and write down what I do know and get some expressions. And then we're looking for eventually mu, right? Mu k. So I know that I eventually have to get to friction. But we have to kind of just like now sit and play with the different net force equations until we can get something for friction. So I plug in my MA in each of the directions. We know that in the y direction, the block isn't like floating up into the air on the y-axis, and it's not like crushing into the ground. So in the y direction, the sum of forces is 0. In the x direction, we know it's accelerating. Okay, from here, we're just, like I said, we're going to kind of just play around and sub some stuff in and solve. So I know because I'm looking for my coefficient of kinetic friction, I'm eventually going to want to plug in mu times the normal force for my frictional force into my x equation here, and then just continuing to kind of sub in what I know. I plug in my mg for my weight here, and then do some algebra, get an answer. So these problems are definitely challenging. And if it's something that's super algebra heavy, I always encourage you to save that for last. Just get your, like if this were a free response question, get your net force equations written, plug in what you know for F equals ma, and then maybe you come back and do this algebraic manipulation to get to an answer. You do that last, just because it's going to take a minute, right? Okay, great. So the last one here is universal gravitation. So this is, like I said, kind of random, but I wanted to at least show you this formula so that you see it, you know what it means, and that way when you see, I feel like there's usually like one multiple choice question or so on the test around using this formula. So I want you to like, especially, I saw some notes in there about how like maybe we haven't seen Unit 7 yet. A lot of it, you can just use the rules of the other units that you have done. And we'll talk about that as I kind of continue on. I've sprinkled in some other Unit 7 stuff, but this is kind of a very unique thing, so I wanted to talk about it specifically. So for universal gravitation, the definition of it is basically like everything we talk about with weight and with gravity is happening close to the surface of the Earth or the surface of whatever planet you're on. All of those rules that we talk about apply when you're close to the surface of the planet. More generally, we can talk about the force of gravity using universal gravitation. And the definition, which I know I said before, but here I'm really going to give it to you, is this idea that any two masses, no matter how massive they are or how not massive they are, it's going to exert an attractive force on each other. So mass will always exert attractive forces on other masses. And there's a formula, Newton's law of universal gravitation, this one, that tells you the amount of force that's attracted. So if we unpack it, all it's saying is we're going to multiply big G. Big G is a constant. It's on your equation sheet. I pointed it out at the beginning. It's on that first page. And it's the number for it is 6.67 times 10 to the negative 11th, but you don't need to memorize it. It's on that page. You would just plug it in. Big G times the mass of the first object times the mass of the second object divided by R. And R, we have to be careful, R in this case is not the radius. R in this case is the distance between the two masses, and then it's squared. So R is not the radius of one of the masses. R is the distance between the two masses. I hate that they have R here. I would put D there because it's a distance between the two masses. So just remember, it's not the radius of one of the circles, it's the distance between the two masses, and it's squared. So frequently you'll see problems with this that are asking you about, like, what happens if you double the distance between the masses, or you double the mass of one of the objects? And it's going to be kind of those like proportional questions to figure out. Remember that if you can't just eyeball it, which a lot of times I can't just eyeball it. That's just not how my brain works. You can always plug in numbers for those sorts of things, right? So if they say double the mass, make the first mass 1 and the second mass 2. You doubled it. See what happens to the force. Or if they double the radius, make the first radius 1, the second radius 2, or the first radius 2, the second radius 4. Like mathematically double it and then just see what happens to the number in order to answer the question. Okay, good. We're looking great. So here we are coming on to our first full free response practice. So we have a whole thing here. This one comes from 2007. This was one of the questions in 2007. And you've got, this is a forces question primarily, right? This is the whole thing. So it's asking you, we've got the block propelled along a rough horizontal forces. We've got some expressions, draw a free body diagram, derive an expression for the normal force, derive an expression for the coefficient of kinetic friction, sketch graphs of the speed and the displacement, and then down here, derive an expression for the magnitude of the greatest acceleration A the block can still have and main contact with the ground. So how we're going to treat these, I've got a couple of them sprinkled through, and we'll see how many we can do in these 5 hours, but I'm going to give you 15 minutes. I'm going to set an alarm on my phone for 15 minutes. I'm going to go quiet so that way you can concentrate. You're going to have 15 minutes to do it. And I'll tell you when, the time that it will be over. And then on the next couple of slides, I have the scoring rubric that they used to grade this problem. And so I'll talk through the answers and I'll give you a chance to score yourself to see how you did. So you can see hopefully how much this problem connects to the ideas we were just talking about. So hopefully you've got a little bit of a leg up as you're working on it. But like I said, I'm going to give you I'm going to give you 15 minutes to complete it, and I'm going to set an alarm on my phone. So you're going to hear, maybe, depending on how well my mic is, an alarm go off in 15 minutes to be done. So I'm going to hit the start button in just a second. You'll have 15 minutes. I'm going to go quiet. You're going to work on it, and then we're going to go over it together. Okay, start. As a time check, we've got just about 5 minutes left. All right, y'all. I don't know if you can hear that or not, but that is your time. So hopefully we got through all of A through E. If not, that's okay. This is why we're doing it, right? It's practice. So you can kind of feel what that 15-minute chunk of time will feel like. So that way you kind of can feel out your pacing and where you're at, and maybe whether or not we need to move a little bit faster or move a little bit slower if we were done with extra time left. So let's spend a couple of minutes actually going over what the scoring guidelines for this problem were. So I'm going to start cruising through the next couple of slides. And what I encourage you to do is, as I talk through the answers for each of the A through E, check your work and check and see if you would have gotten all of the points for each of the letters. And if not, figure out obviously where you went awry, and you can fix it for next time. So let's spend a couple minutes doing that. So for A, you can see it is 4 points, and it's just for each of the forces, right? So it asks for a free body diagram. You get a point for each of the 4 forces shown above. The arrow has to be correctly drawn, so that means it has to be pointing outward, and it's got to be labeled with the force. You also see here that if there was an incorrect or an extraneous vector, such as an acceleration vector or a velocity vector, you would deduct a point. So you could get anywhere from between 0 and 4 for part A, depending on if your free body diagram looked the way it was supposed to. So take a second and score yourself here. Give you just a moment to do that, and then we'll go to B. Okay, great. So let's look at B. So B, I don't know what B says. B says, derive an expression for the normal force exerted by the surface of the block. So looks like the easiest way to get all of your points for B, the first one is writing the correct Y component. So making sure that you've got F1 sine of theta for your Y component of F1, and then you get a point for the correct answer. So you should have, to get both of your points, you have to have done F1 sine theta, and then you should have an expression N equals mg minus F1 sine theta. And it was worth 2 points for this one. So take a second and score yourself here. Okay. C asks for the coefficient of friction. So this one was worth 3 points. You get 1 point for showing the correct expression for the horizontal forces, setting them equal to MA1. So that's this right here, right? So F1 cosine theta minus mu times the normal force gives you MA sub 1 here. So you get a point for that. You get a point for substituting in the expression for the normal force from the last letter. So putting in what you got for the normal force. And then you get 1 point for a correct answer. I also want to point out in this moment, as you're working through this, because there's partial credit, there's the potential that maybe you didn't get B right, but you still could have gotten this point in C. So it just says substituting the expression for N from part B. Your expression for N could be wrong, and you put it in here, you still would get some points, right? So I just want to, point out that the partial credit is real, right? Kind of throughout, even if you didn't get all of them right, even if you had you were like, I don't really know what to do in this one, writing something down, and even just writing this net force expression and setting it equal to MA would have gotten you a point. So definitely, you'll hear me say this a lot in the next few hours, write something down for these free response questions, even if you don't get fully to a correct answer. Okay. D. So D asks you to sketch some graphs. So the first one, you get a point for a linear relationship of the V versus T graph with a positive slope and an intercept at 0, right? So V0 at T0. So the line had to start at 0, 0 on the graph, and then go as a positive a line with a positive slope right here. For the position time graph, it says it's got to be a parabolic, right? So it's got to be a parabola. It's got to look like this as a parabola. It's concave upward, so it's got to be concave in this direction. If you drew something that went concave down, you wouldn't get this point. And then it has to start at 0, 0 as well. And then the two graphs have to be consistent with one another. So basically what that means is if we look at the position graph and we took its derivative, it should look like the velocity graph. Or if we look at the velocity graph and we integrate, it should look like the position graph. Have to be consistent with each other. That's D. So take a second and score yourself here. Okay, and then E was kind of it's only worth 3 points, but this is the one that had a lot of algebra in it. So E, I believe, asks you to find an expression for the maximum acceleration before it would lift off of the ground. So you got 1 point for just recognizing that that maximum acceleration at that point, the normal force is equal to 0. That's kind of like optimizing or maximizing what that acceleration would be. That's kind of the theory behind it, and you get a point for just recognizing that. You then take that idea, and we recognize that if the normal force is 0, then the frictional force has to also be 0, right? So you get a point for recognizing that, and then you get a point for the correct answer. So you actually could get 2 out of the 3 points before you do all of this algebra by just recognizing that the normal force is 0 and the friction is 0. And then you get 1 point for doing all the algebra. So again, right, even if we didn't finish all of it, depending on how that 15 minutes went, getting something down and even just like moving in the correct direction is going to help you as you take this test. So make sure you do it, right? Write down what you know. You've been studying so hard, so write down what you know. Okay, great. So last thing before we take our next break, we will go back to this equation sheet. So I'm going to share my screen differently again. Switch it over. And you can see here, hello, hello, still here. Let's take a relook at this equation sheet after we're done talking about forces. So we have added, we've already looked at those 3. We've added this one. So this is Newton's second law, right? We talked about that a lot in the last hour. There are some other forces here. We haven't talked about them yet. We have talked about this one, though. We talked about the force of friction. So this equation now is check, done. We've talked about that one. If we scroll, I think there's only one more, and I think it's just this one. So we went here and we talked about Hooke's law, right? We talked about restoring force in the mass on the spring, mass spring oscillators. We talked about spring constant, distance stretched or compressed. Oh, and we talked about universal gravitation down here. Fg equals g m1 m2 over r squared. So we're slowly checking the boxes here. I feel like forces, everything just comes back to Newton's second law, right? So while it's, not a lot of different things on this equation sheet, Newton's second law is a big check mark. So hopefully we feel a little bit better after this last hour of forces, because we are about to head into the next topic. So let me switch this back over. See me dancing. Okay, great. So you all have been working super hard. So again, we're going to take a 5-minute break. So you take 5 minutes and get up and get a snack and get some water. It's important as we're studying to make sure that we're also taking care of ourselves, right? So let's see, it is 06 right now. So it's 2:06 by me, but it's 06 right now. So we'll all come back here at 11. So for me, it will be 2:11. And the next topic we're going to talk about is energy and momentum. So take 5, and then we will continue on from there.
All right, welcome back. Welcome back. I think as we are now entering hour 3 of our 5-hour cram, things are about to get good and also a little loopy, I think, as we continue. So one of the things that we're going to start doing as we come back from these breaks, and I'm going to try to kind of like intersperse them as we continue in these next few hours, is some fun poll questions just to keep the brain moving. And yeah, on your toes. So I've got some would you rathers. Let's do one now just to get us all back in the zone before we start talking about energy and momentum. So we're going to start easy, and I think, at least from my perspective, they're going to get harder as we go. So this is an easy one, I hope. So why don't you take a second and just let me know that you're back. Answer this question. Would you rather get a pet dog or, oh, we are flying with our answers. Would you rather get a pet dog or a pet cat? Take a second and give me an answer for that one.
I have a very, very strong opinion about this, but would love to see if we're dog people or if we're cat people here. Take another 10 seconds or so to answer. Okay, it's trending in the direction that I want it to. I'm just gonna, I don't know, I feel like you're gonna have to wait and see, but yeah, good. People feel very strongly about this, I think. Awesome. Okay, so votes are slowing down, so I'm gonna show you the answer, or there's no answer. Show you the result here. I think not overwhelmingly, like it's we have a solid cat showing, but overall, I think most people say dog. I agree. Although I will say that I'm actually allergic to most animals, and so really, like, I like to look at them, but if I get too close, I start sneezing. So that's me. But awesome, we are dog people. Okay, we're gonna, like I said, we're gonna kind of start to intersperse those in the next few hours, just to keep ourselves on our toes. And I know I feel like I get a little loopy the longer I study. So just trying to keep you on your toes a little bit and give you some brain breaks. Okay, so here we are. We are in the 2 o'clock hour on the East Coast, which for me means conservation of energy and momentum. So this is a lot. This is kind of 2 units that we're going to smush into one and just talk about the big ideas from both of them. And the reason I put them together is because a lot of the ideas are parallels to each other, right? So I'll show you what I mean by that. But we can think about energy and we can think about momentum in similar ways a lot of the time. And hopefully that kind of helps with, as you're strategizing when you're looking at problems, you can kind of like be like, oh, this one's kind of like an energy and a momentum, and they're kind of the same. I'll show you what I mean. So first, let's talk about energy. First thing we'll do is go into work and energy. So we'll talk about work, what it is. We'll talk about the work energy theorem. And then in 30 seconds, I'm going to talk about power. So work, definition of it, it's an energy transfer. Energy is defined as a change in work. So it's a very circular thing, but how we define it is an energy transfer. And the way that it works, no pun intended, is that it's caused by a force. So that's why it comes next, right? We just talked about forces. Now we're going to talk about energy and work. Work is caused by a force being applied over a specific displacement. So they have to be moving they have to be pointing in the same direction. So the only force, like in this example here, the only force that's going to cause work is going to be the component of the force that's pointing in the same direction as the object is moving. If the force is constant, then the work is going to be equal to FD cosine theta. That is a simplification of what we see down here as the dot product. Remember that when we have the dot product, we take each of the numbers that we're looking for, and we multiply by the cosine of the angle between them. If it's constant, we can just not worry about the integrating here. We can just do the force times the displacement times the cosine of the angle between them. If the force is changing, however, we do need to integrate. The work is equal to the force with the dot product of the position, the derivative of position, right? So it's, sorry, again, loopy. We're going to integrate the force with respect to the position. That's what I meant to say. This formula is on your equation sheet. And work is going to be measured in joules. So here's a little graph for you here. If we look at it in terms of the graph, we know that when we integrate, we take the area under the curve, right? So whether that is, if it's curvy like this, we'll have to do the math and actually get an integration with numbers. If it's something that's like more geometric, you can always just find the area of the under the curve, just like geometrically as well. Work itself is a scalar quantity. And what that means is that we're just going to look and see if it's a positive sign or if it's a negative sign. And there's some rules here, right? So this is all just coming from the equation that we looked at on the last slide. But sometimes it's helpful to kind of just like draw it out and envision it, which is why we've got this slide here for you. So If the force is perpendicular to the motion, the force is pointing in one way, the motion is 90 degrees, or the displacement is 90 degrees from the motion, the work is going to be 0. So that's this example right here. The work is 0 because F is pointing up and the displacement is pointing in a 90-degree angle from that. So there's no work done. The cosine of the angle between them is 0. If the force is in the same direction as the motion, the work is going to be positive. If they're in opposite directions, the work is going to be negative. And then if the object isn't moving, there's no displacement. And if there's no displacement, then the work is 0 as well. That's something that I think, you can push on something, but if it doesn't move, then there's no work being done. It has to have a displacement. So why do we care about the work? The reason we care about the work is because work is going to change the energy of the system. If we've got positive work, we're inputting energy into the system. If we've got negative work, we're taking energy out of the system. So we can relate them together. And this is the formula. It's on your equation sheet. This is called the work energy theorem. All it says is that the change in energy is equal to the work. And then this is actually, we looked at this part of the equation on the last slide. I just kind of covered up the first part because we hadn't gotten there yet. Now we're here. So the change in energy is equal to the work, which is equal to the integral of the force with respect to position. I do know how to say that. So this is the relationship between them. So if we can either find the change in energy and set it equal, and that's equal to the work, or if we find the work, we know the work is equal to the change in energy. Energy is measured in joules. So there's some specific types of energy, right? So the first one is kinetic energy. Kinetic energy is the energy of motion. We can use this formula to calculate it, symbolize it with a capital K. It's dependent on the mass of the object and the velocity of the object, or the speed of the object. Sorry, the speed of the object squared. Okay. So let's do this first example in this section. So we've got a person throws a ball. We know the ball's mass starts from rest, accelerates horizontally and uniformly through the distance of 0.9 meters, leaves the person's hand at 30 meters per second. So we need to find the horizontal force applied to the ball by the person's hand. So this is a work energy theorem question. We need to know about the kinetic energy of the ball. We need to know about the work done on the ball in order to find the force. So let me open up a poll here and see what y'all have for this. Okay. Go ahead and take a minute and see if we can get an answer for this one. All right, we've got some votes coming in. Take another 20 seconds or so. All right. Okay, if you're going to vote, last chance. Okay, great. Great. So overall, again, y'all overall totally got it right. So good work, team. The correct answer here was D, 100 newtons. So let's take a second and look at it. So what we're going to do here is recognize that we're looking for a force. We're given a distance over which that force is applied. We're given the mass of the ball, and we're given the velocities of the ball. So that there's really two ways we could solve it. You could use like a kinematics, Newton's second law. You could go through all of those things to figure it out. But I think a big theme that I want to share with you today, as we're thinking about efficiency on the test, is that frequently solving problems using energy when you can is going to be faster. Energy is typically quicker. You don't have to worry about components as much, and you're just kind of like cruising through the different types of energy. So this is an example where solving it with energy is going to be probably faster. The only energies that's going on in this problem is kinetic, right? Starts with no kinetic energy, leaves the person's hand with a certain amount of kinetic energy that we could calculate. And that change in energy is going to be equal to the work. So we're going to use this delta K, because it's only kinetic energy, is equal to the work. And then from there, we're going to solve for the force. So I find my change in energy by plugging in my mass and my speeds. I set it equal to the force times the distance times the cosine of the angle between them. And then from there, I would just solve for force, and we get 100 newtons. Answer is D. Okay. This is my 30 seconds on power. You are probably not going to see power on this test. If you do, it's going to be like one multiple choice question, probably. Although now that I say it, you know that they're gonna throw something else at you. But I probably jinxed it. But power is not super prevalent, but you do maybe see a multiple choice. All it is it's the rate of energy transfer. You've got two formulas to calculate it on your equation sheet. We either take the derivative of the energy function with respect to time, or we multiply the force vector times the velocity. Yeah, that's it. It's measured in watts, and we can use it to figure out basically how much the energy is changing, or how fast the energy is changing, how much the energy changes per second. That's what power is. Okay, this is going to be much more important, and you're going to see it a lot more on the test. So we need to talk about conservative forces. We need to talk about potential energy. This is something that always comes up. It's an important one. So we need to make sure that we really dive into it in the next little bit, so that way you know what you're doing. There's also a formula here that is not on your equation sheet that always comes up that you're going to need to write down. So be ready for that. I'll cue you when it's time. First, though, let's talk about conservative and non-conservative forces. So a conservative force happens when the object's path doesn't matter. If an object is moving through some sort of closed path and returns to its initial position, so I think of it like if you're on like a track and you run a lap around the track and then you come back to zero, if the path affects the work, because the work has to do with the displacement, right? But if the path affects the work, then it is a non-conservative force. If the path doesn't matter, then it's a conservative force. So the two conservative forces that are relevant for your lives in terms of this test are going to be gravity and elastic force. Anytime we see that, those don't affect the work. They don't affect the energy in the system. The ones that do, that we have to care about, are the non-conservative forces. The work done is not zero. The work is, this should say non-conservative. That's a typo. And the object's path matters. And if we think about it, that makes sense, right? Because if we go around the track, there's going to be friction. And if the path that you take around the track is like the inside lap versus the outside lap, you're going to hit more friction around the outside lap than you are around the inside lap because it's longer. And so you're going to have a bigger frictional force, and it's going to change the energy in the system. Drag force, we know, is just like another example of a frictional force. So it is also a non-conservative force. So the big ones that we have to care about are frictional force, and then drag force is like a sub of frictional force. Here's a different way to look at it. This is a great picture. So if we look at these three different paths, there's the red path, the green path, and the blue path. If it's a conservative force, then the work done through all three of those paths will be the same. If it's a non-conservative force, the work done is not the same. The path matters. So who cares? Why do we care about this? The reason we care about this is because of its relationship to energy. Remember that potential energy in general is the energy an object has due to its position. And we can relate it to conservative forces using this equation that I've boxed here on the left. This is the equation that I want to signal to you right now, to cue to you. It is not on your equation sheet, but it is incredibly important. It comes up every single test, and you need to remember this relationship. So if this is not written down, if this is not in your brain, put it in your brain. But in the meantime, at least write it down so that way you can put it in your brain tonight. And what it says is that the conservative force, so it's gravity or it's spring force, is going to be equal to the negative derivative of the potential energy with respect to position here. So if we've got a potential energy function, which I'll show you in a minute, if we've got a potential energy function, we can take its derivative, make it negative, and that's going to be equal to the force, the conservative force acting. Important. I think there's a couple of multiple choice examples that I threw in here in a second. For sidebar here, gravitational potential energy, it's the energy of an object due to its position relative to Earth. This is the equation for it. This is, I will caveat here, this is when the object is close to the surface of the Earth. Most of the things you're going to do, unless it specifically says it's not, you're going to use this formula. There is another potential energy formula that I'll show you for, if we're talking like universal gravitation, masses of planets, those sorts of things. But for anything on Earth that's close to the surface of the Earth, so like most of the physics you're doing, this is your potential energy formula. Relates the mass, g, and then the change in height in meters. Oh, here's the sidebar. Yeah. So again, most of the time you're using this one. If you're talking about something, if they ask you something about like, there's a satellite or two planets or a meteor orbiting or a comet or something like in space, you also have this potential energy function that's like a more generalized version. So if we look at it, it's negative big G, remember that's universal gravitational constant, the mass of the two objects over, and then R again is the distance between the objects. It's not the radius. So if we wanted to find the potential energy between two objects, generally we use this. Most of the time, assuming it's not like not like in space, we would use this first equation. Okay, so here's an example of when we're going to use that new formula that's not on your equation sheet. We're given a potential energy function. We know B and C are constants. Which of the following is an expression for the force of the particle? So take a second and I'll go back for a second. We're going to use this equation to solve it. So hopefully we've written it down at this point, but there it is one more time. You're going to find the expression for the force on the particle. And I'm going to open up another poll. Give me 1 second. Okay. So take about 30 seconds to work on this one. Great, just take another couple of seconds to vote if you haven't. Awesome. Y'all, this one's so good. Look, let me show you. So many of us got it right. Amazing. Great work, team. So this equation, this relationship is super important and you all know how to use it. So that's awesome. If you're someone who didn't get it right, we're going to talk about it right now. That's okay too. Let me just show you how to do it. So I feel like when you look at this potential energy function at the beginning, you're like, a lot of letters, a little intimidating. But remember that B and C are constants. So we just treat them like numbers, right? So it's asking us to relate this potential energy function to the force function. And we're going to use this relationship to do it, this f of x equals negative du dx. So all we need to do is take the derivative of the potential energy function and then make it negative. So remember that if it's a constant, we treat it like a number. So the first thing to take the derivative, I'm going to move the negative 3/2 in front, and then I'm going to subtract the exponent by 1. So we get negative 3/2. B is just a number, it's constant, it just stays there. R to the negative 5/2. And then C here, C is also a constant. And when you take the derivative of a constant, when you take the derivative of a number, it's just 0. So that just goes away. Finally, we just make it negative. So it starts negative because the exponent's negative. 2 negatives make a positive. So our final answer is 3/2 BR to the negative 5/2, which is A. Great. Okay, so let's talk about conservation of energy. So first, what is it? Ryan here is pointing to it because it's super important. You're going to see it for sure tomorrow. So all it says is that the total energy in the system remains constant. Another way to say it is if there's only conservative forces acting on the system, then the total energy of the system must be the same. So once you have non-conservative forces, so once there's like friction and stuff, we have to take that into account. But assuming that there isn't any friction, there's only conservative forces, then the total energy of the system always has to stay the same. So I don't know if you've ever, like, if you were taking this class, maybe your physics teacher did it, or maybe you've just seen it on the internet, but there's this really classic bowling ball pendulum experiment where if you start the ball at rest, this is Neil deGrasse Tyson, right, at his face, we know because of the law of conservation of energy, it starts with max potential energy, so it can't go any higher, right? So he can just stay there and he can trust in physics that it's not going to hit him because of the law of conservation of energy. So whenever I think of conservation of energy, this is what I picture as a way to help me remember about what it means, right? The total kinetic plus the total potential has to always equal 0. Alternatively, when we add them all up, it has to be the same every time. Okay, so you're not going to do this one. I'm just going to talk through it. But this is a free response question from 2009 that has to do with this combination of conservation of energy and having this energy function and dealing with like the force and stuff. I also, yeah, great. I also want to point out that this is going to be a simple harmonic motion question. And so I want to just say that now because I know there were some people asking about simple harmonic motion. This is another way that it kind of like sneaks in. And we'll talk about that. So here we go. We've got the 3 kilogram object moving along the x-axis in the region. We've got a potential energy as a function of x, 4x squared. Object passes the point x equals negative 0.5 meters. Its velocity is positive 2 meters per second. And it says all forces acting on the object are conservative. When you see that all forces acting on the object are conservative, that is telling you energy is conserved. Conservation of energy problem. Mark it. That's great. Okay, so for this first one, I think it says, what's the total mechanical energy of the system? So all I need to do is figure out the total potential energy and then the total kinetic energy and then add them up. So I'm given enough information to find each of them. I'm given the potential energy function and where the object is. So I know I know X, right? And I know the function to find my potential energy. And then for the kinetic energy, I'm given the mass and I'm given the speed. So I can plug that into my equation as well. So from here, all I did is plug in what I knew into my potential energy function, found out that was 1 joule, plugged in what I knew to my kinetic energy equation, found out the kinetic energy at that point is 6 joules. So my total energy is going to be 7 joules total. For B, it asks you to calculate the x coordinate of any points in which the object has 0 kinetic energy. So again, we know that energy is conserved in this problem. So that means the total energy at any point in this motion is going to be 7 joules. So if the kinetic energy is 0, then all of the energy is potential. And so we know that the 7 has to be equal to the potential energy. So I can just plug in 7 for the potential energy and solve for x. Remember that when you take a square root, you can do the plus or the minus, right? Okay, great. So then this last one here, look at the magnitude of the acceleration of the object as it passes x equals 0.6. So in order to do that, we need to now use the that relationship between force and energy, because it's all conservative, right? So the first thing that we can do is take the negative derivative of the potential energy function to find the force function. So if I do that, I get negative 8x. And then that force is the force exerted on the system, so I can plug it into F equals ma, and I can solve for the acceleration. I get an expression for the acceleration in terms of x, and then I know it's at 0.6, and so I can get a number for a eventually. The reason that I know this is simple harmonic motion, and I think this is the next slide, but the reason I know that it's simple harmonic motion is if I look at this potential energy function here, it's 4x squared. And so we're going to see that this x squared, potential energy equals something x squared, is going to be what potential energy functions for simple harmonic motion, specifically mass on a spring, look like. So I hinted at, we're going to skip this. I hinted at the fact that I knew that it was potential energy, or it was a simple harmonic oscillator, and this is why. So couple of things, just revisiting simple harmonic motion here. First one, we talked about this idea of Hooke's law and spring force, but I put it here too. I know you have access to these slides, so as you're kind of going through, I'm trying to kind of make sure to put the spring stuff together for you, right? So we talked about spring force, and this is spring potential energy. So the formula for spring potential energy is 1/2 times k times x squared. So we talked about k as the spring constant, x is the distance the spring is stretched and compressed, and that's how we find the potential energy in springs specifically. Okay, we're going to pause. We do need to move on to momentum, but again, I want to take a minute and just keep your brain working. So we're going to do another fun question here. So we're going to do 2. I'm feeling spicy right now. Let's continue in the animal realm, kind of. This is a stretch, but let's do this one. So would you rather have a pet dragon or a pet unicorn? Where are we at? What do we want? Take a second and vote. Great. I think most of us are in. If you're not in, take just another moment. I know it's a hard decision. Okay, great. Awesome. Most of us are firmly in the dragon camp. I think I agree. Dragons are kind of cool. Although, I mean, unicorns are pretty too. So I don't think there was a wrong answer there. What about this one? Would you rather sound like a sheep? Or a chicken? when you laugh? Sheep or chicken when you laugh? Take another second to vote. Would you rather sound like a sheep or a chicken? We have a pretty overwhelming majority for this one, and I think I agree with you all again. Okay, it looks like the voting has slowed down. So this is where we landed. Most of us very much think sheep. I think I agree with you again. Although chicken could be kind of crazy. Like, I don't know. I feel like it depends on how much attention you want, I think maybe. Okay, great. Cool. So thank you for playing my game. Let's continue on with momentum. So we're going to cruise through some momentum highlights here. And then I think I have another full free response for you. So I think that's what's coming next. So first, impulse and momentum. So the reason that I was like, they're kind of in parallel with energy, because I always think of it like work and energy and then impulse and momentum. They function kind of similarly in that mathematically the graph, like when you have the graph, you kind of do the same thing for both. And so I want to just briefly talk about it, and I'll kind of show you what I mean by how it kind of works like work and energy. So momentum first. Momentum is it has this very fancy definition as the quantity of motion, which to me doesn't actually like mean that much. Really, what I care about is the formula. So momentum we symbolize with a P, and it's going to be equal to the mass of the object times the velocity of the object. Notice those vector symbols. Momentum is a vector, and we're looking now at velocity, not speed. So we were talking about like kinetic energy and speed, but momentum, we deal with velocity. Our units are kilograms meters per second. That should make sense because our masses are in kilograms and our velocities are in meters per second. And changes in momentum are caused by forces. So here's another force equation. Forces just don't go away. If a force acts on a particle, changes the particle's momentum. So this is the relationship. Force is equal to the derivative of momentum with respect to time. Here, this formula is also on your equation sheet. Impulse is the name that we give to the effect of that force that acts on the object over time. So we symbolize it with a J, and it's equal to the integral of the force with respect to time. And this J, this impulse, is equal to the change in momentum. So just like work is equal to the change in energy, impulse is equal to the change in momentum. And the way we can find it on a graph is integrating or finding the area under the curve if it's something that's geometric, like you could do it with this. So here is another example, another practice for you. So we've got identical net forces acting for the same length of time. So same force, same time on two different masses. Which of the following describes the change in linear momentum of the smaller mass compared to the larger mass? So you are going to use impulse momentum in order to figure that out. So take a second and let's do this practice problem. Let me open up a poll for you. Great. Take a minute and answer this one. I know it's a lot of words. Take a second to read it. All right. Take another couple seconds if you're going to vote. All right, great. So overall, we got this one right too. Go team, although it was a little bit more split. So let's talk about it. So the answer here is C. And most of us got it. Good work. But some of us didn't. So let's talk about why the answer is C. So if we take a look at this, we really have to just think about what's the thing that's going to affect the momentum, or the change in momentum. So we are told that the force and the time is identical. The only thing different between the two masses is that their mass is different, right? The two objects is that their mass is different. If the force and the time are the same, then the impulse by the formula has to be the same. We know that impulse is equal to change in momentum. And so we know that if the impulse is the same, the change in momentum must also be the same. That's going to be different than the value for each individual momentum themselves, like the before and the after, because the larger mass has a bigger momentum, but that change in momentum is going to be the same for both. So it's like a small, and it's kind of like an annoying difference, but we have to just think about it in terms of the formula, and we need to recognize that the actual number for the momentums themselves are not always going to work the same way as the change in momentum. Yeah, that's what I'd say about that. Okay, let's do another one. So we've got graph given here. Force of an object of mass m is a function of time. For the time interval 0 to 4, what's the total change in momentum? So again, this is a change in momentum question. So we're asking about impulse and momentum. So let me open up this one. Right there. Great, we've already got some answers in. If you're still thinking, take about 30 seconds here. Okay, if you're going to vote in the next couple seconds. Awesome, y'all. So let me show you what happened. So great. Almost everyone got it right. Let's still talk about it just because we leave no peer behind. We gotta make sure everyone knows, right? So let's talk about it, but overall looks really good. So the easiest way to solve this is to think about it in terms of rectangles here, right? So we know that to find the change in momentum, we need to integrate the force with respect to time. We also know that the definition of integrating is the area under the curve. So what we can do is just find the area under the curve from 0 to 4. And it's a rectangle, so you can just mathematically do it. We can also just eyeball it. So if you look at it, we see that this area and this area are equal. This area is above the curve. This area is below the curve. So you're going to subtract them out, right? They're going to cancel each other out, and you're going to get 0. So your answer is C here. You could mathematically do it too. If you wanted to, you could find that the change in momentum above the curve is 20, change in momentum below the curve is negative 20, which if you add them together gives you 0. Great. So let's talk about conservation. So conservation of momentum. So this is perhaps one of my favorite memes that I will show you today. I love The Office, and so I think this is so funny. The idea of conservation of momentum is that exactly what it sounds like. Momentum is always conserved. So it has to be an isolated system, just like conservation of energy, right? So in both energy and momentum, there has to be no non-conservative forces. So basically that means there's no like forces applied into the system or friction taking energy or momentum away from the system. So as long as it's isolated, momentum is always going to be conserved. Momentum is going to remain constant, and the initial momentum is going to be equal to the final momentum. So these two pictures are the same, right? So I always think of it in terms of, I don't know if you've seen one of these, it's a Newton's cradle. This is a great example of momentum transfer within a system. And then this picture on the right, and I'm kind of going faster because I want to make sure we can make sure we get to everything in the next few hours. But this picture on the right, I wanted to specifically talk about because when we look at conservation of momentum, we're going to look at collisions. And there's both collisions that with objects that start apart and then collide, but there's also, we count it as a collision when it's like this. I think of it like an exploding problem. The teachers start together and then they push apart. And we also see that the total momentum is going to be the same because in this, it looks like, I mean, this is, well, the difference between the first picture and the second picture is that there's the second guy down here, right, who's increasing the mass. And if he's increasing the mass, the speed of the two teacher object is going to be slower because the momentum has to be conserved. So that's what you're seeing in these two pictures as they're being compared. I also think this comic is funny, just continuing to find some joy in our last minute cramming. Because this is, a science teacher monitoring research and creating a Newton's cradle. I promise I've never done that. Okay, great. So one way to approach solving conservation of momentum problems is to create a table. So what you can do is you can figure out the momentum of each object before, add it up to find a total, and then recognize that that total has to stay the same, and you kind of fill in the other boxes for after based on what you know. Or if they give you info about after, do that with before. But this table is one way to kind of organize all of the different momentums of the different objects as you're looking at collisions, if that's something that that's helpful to you. There's different types of collisions. So I think of it kind of on this like spectrum here. The two kind of main types that we talk about in mechanics are elastic collisions and then something called a perfectly inelastic collision. Elastic collisions, the big rule with elastic collisions is that the total kinetic energy in an elastic collision is conserved. So the initial kinetic energy is going to be equal to the final kinetic energy. Frequently, the example that they use for that is going to be like billiard balls, pool balls, right? So this is my little GIF showing you pool balls. The opposite of that is going to be a perfectly inelastic collision when the two objects start apart and then they collide and then they stick together. In this situation, the kinetic energy is not conserved. And in fact, in any inelastic collision, the kinetic energy is not conserved. Most macroscopic collisions in real life are going to be inelastic. Things will collide, we'll lose energy we'll lose kinetic energy to turn it into like sound or light or heat or like fire, I guess, if something starts on fire. But most things are inelastic, but the problem will tell you, if it's elastic, then you got this, it's signaling you that the total kinetic energy is conserved. If it says perfectly inelastic, that means it sticks together. And then if it's just straight up, either doesn't tell you or it tells you inelastic, then we know that the total kinetic energy is not conserved. Okay, so let's apply that here. So we've got an object moving on a horizontal frictionless surface, makes a glancing collision with another object initially at rest. So we say glancing. Glancing does not tell you elastic or inelastic, right? We don't know. In this case, which of the following is true about momentum and kinetic energy? So this is another one of those conceptual questions, no math involved. Let me open up a poll here and see what y'all think about this. Really just gotta get there. Hold on. There we go. So take about 30 seconds here. Just another couple seconds. Awesome. Awesome, awesome. Great work, go team. Let me show you. Overwhelmingly got it right. Answer is A. Momentum is always conserved. Always, always, always. Kinetic energy may be conserved. We don't have enough information about whether it's an elastic collision or an inelastic collision to decide. So that's exactly what I just said, right? No friction, so because it says frictionless. So there's no non-conservative forces. Momentum is conserved. We don't know enough to determine if kinetic energy is also conserved. Okay, so again, just continuing to emphasize momentum is always conserved. This one I thought was funny because as the fish sneezed, it went left, and so the other one had to go right in the fish tank. Great. And then just another way to picture, trying to give you lots of pictures of these collisions, could be pool billiard balls colliding, or another example that they sometimes use are like trains coupling and then sticking together. That would be an example of an inelastic collision. Okay, let's do this one. So this one will ask you to do a little bit of math. So take a second, and this is a conservation of momentum question. The cars are going to stick together and find the speed of the cars together after the collision. Take another few seconds. All right, great. So overall, again, really, you guys, it's so good. You're going to be so good. Overall, absolutely got this one right. Correct answer is A here. And let's take a look at the math real fast to check it out. So if we take a look, we know that the momentum is conserved. So I created one of those momentum tables to help me keep track. You don't have to. It could be like, it's really up to you. If your brain works better that way, do it. Could be more trouble than it's worth. Really, the steps here were to find the momentum of each object individually, remembering that we have to take direction into account, right? Because it's a vector. So rolling, the second one is rolling to the left at 3 meters per second. So I made that one negative because it's moving in the negative x direction. So we do that. We get a total momentum initially. We recognize that total momentum has to be true after the collision. And then from there, if they're stuck together, then the new total momentum has to be the masses added together. And so I added the masses, multiplied it by this new speed, and then solved for the velocity. I mean, not the speed, the velocity. I got a negative 2/3 meters per second. It asks for the speed. We know that speed doesn't have a direction, right? So I just made it positive. Speed can't be negative. And so our final answer is A. Okay, and then just a minute on 2D collisions. when we look at 2D collisions, we have to remember that momentum is conserved independently in each dimension. So just like everything else, keep it separate, make a separate momentum table for each dimension, and find the components of the velocity vectors in each dimension, both before and after. So 2Ds are kind of a doozy. If you get stuck with a 2D collision, that's a big one. But there's kind of a lot of parts, but hopefully a lot of them are going to be conceptual. So we're not going to spend time doing this one individually. I'm just going to talk about it just because I'm sensitive to the fact that we need to continue on. But here, this is a 2D question. So object having an initial momentum that looks like the vector above strikes an object at rest. Which of the following sets of vectors may represent the moment of inertia, the momenta of the two objects after the collision? And all this is asking you is to figure out which of these vectors, when you add them together, look like this, right? Because the momentum has to be conserved. The only answer here is E. This is the only one where if we were to add these vectors head to tail, we would get something that looks like this. These guys would cancel out. That's too big. That one points in the wrong direction. That's all sorts of funky and in the wrong direction. E is your correct answer. Okay, final summary for momentum. Initial momentum always equals final momentum. We've got the different types of collisions. For all of them, momentum is conserved. For elastic collisions, kinetic energy is also conserved. For the other ones, not so much. Okay, so I think we have time. Let's do it. So we've got 15 minutes for this free response, just like the last one. I'll put a timer on, and then we'll go through the answers. So this is the picture that goes with it. I wanted to make everything as big as I could so you could see it. I'm going to set my timer. You've got 15 minutes to work on it. Then we'll take a break. Then we'll tackle rotation next. So it is, by me, it's 3:04 and some change. So I'm going to hit start now. You have 15 minutes. I'll give you a 5-minute warning. Go to it. Okay, and here's your 5-minute warning. We got 5 more minutes on this problem. Alrighty, folks, that's 15 minutes. Hopefully we are finished. We're going to take a couple minutes and go through the scoring rubric to see how you did. We'll take a quick break and then we will scurry our way into rotation. So there's a lot of parts to this problem for sure, but let's go through and see how we did. So the first question asks you to determine the speed of the dart just before it strikes the block. So 1 point for this. And all we would do here is take the initial speed, get the x component, and get an answer for the speed of the dart at its max height. Next one asks you calculating the horizontal distance between the launching point of the dart and the point on the floor before the block. 2 points here. You would get 1 point for figuring out the time first. This is a kinematics question. You could alternatively use, I think you could probably use energy to figure it out. Or you get 1 point for substituting it in to figure out the correct answer, substituting into the x, right, to figure out the correct answer for x. Next one, here's where the momentum comes in. So C asks for you to find the speed. You get 1 point for just writing conservation of momentum down. And just being like, this is a conservation of momentum problem. Initial momentum equals final momentum. That automatically already gets you a point. So as we keep going, I'm just going to keep repeating. Write down what you know, right? That gets you a point, just straight there. You get another point for writing the expression for the totally inelastic collision. And then you get one final point for getting the actual correct number, the 1.4 meters per second. So hopefully we're scoring ourselves as we go. I forgot to pause last time, but I'll pause here. So that way you can score yourself as you want to. Okay. D is conservation of energy. So we are finding that angle to which it goes. So this one gets a little bit hairier. But again, you get 1 point for just writing down the expression for conservation of energy. So kinetic plus potential equals kinetic plus potential. You get another point for writing an expression for the height of the block. So that's kind of a tricky one because it involves a triangle, but you get a point for just writing that out, and then you get another point for solving. So take a second and see how you did there. Okay, for E, it's asking you for, I think he asks for the period. Time the block when the dart collides with the block and when the block first returns to its initial position. So we get 1 point for figuring out the period of the pendulum, and then a second point for dividing it in half because we're looking for just the time to get back to its initial position. So give yourself points there. And then F is one of these like qualitative questions, right? So the first one, correct answer is increase, larger angle for the block dart system. And there's an example here. It says a more massive dart would cause the speed after the collision with the block to increase. This would make it reach a greater height and the angle would increase. So you get 1 point for just saying increase without any sort of justification. And then you get 1 point for a correct justification. And then for the second part here, the correct answer is stay the same. You get 1 point just for that. And then the second point is a justification. Would not affect the period because of reading. Yes, because of small angle, right? The only thing that would change it would be the length of the string, or if you went to a different planet. We talked about that, I think, back in hour 1 a million years ago when we were talking about motion. Okay, cool. So we are at the end of our energy and momentum space. So I am going to give you a 5-minute stretch break. Know that it's okay. I know we're like a little behind on rotation. It's okay, because I think that the free response tricks and tips are not going to take an hour. So I've kind of intentionally let us go a little long, so that way we've got plenty of time to do rotation and then tips and tricks, and we'll be fine. So it is, in my world, it is almost 3:25. Regardless, we're probably all at 25. So we'll all meet back talking about rotation at 30. So for me, it will be 3:30. For you, it might be 2:30 or 1:30 or wherever you are, but 5 minutes. Alrighty, folks, welcome back. Welcome back, welcome back. We are going to continue on our journey. We're going to talk about rotation next. Before we do, let me know you're back by answering this question. We are going to change. We were in our animal theme. We are now going over towards food. So the next few would you rathers will be about food. Would you rather have all your food be spicy or have all your food be sweet? What do we think? Take a second and vote there. Take another couple seconds if you're going to vote. Yeah, this is hilarious. Let me show you. If you're voting, hopefully we have taken a vote because I'm going to publish it. Y'all, it's so close. This is the first one that's been so close. That's so great. I think I lean towards the sweet category, so maybe that turns into a 52. I don't know, but we are very split on that issue, and I wish that we could talk more about it. Maybe in Discord later we can. Okay, great. So we are going to head into our last big content chunk. We are going to talk about rotation. And basically, I'm going to talk about as much rotation as I can and save the last, I don't know, 30-ish minutes to do final tips and tricks. I don't think we'll need more time than that. So we'll start now. We'll go into the 4 o'clock hour with rotation, and then we'll wrap up with some multiple choice and free response tips and tricks. Rotation's a bit of a doozy. So I want to talk about it I want to get as much of it as I can to you while we're still together and we have this time. So basically with rotation, the thing about rotation is that all of the other ideas we've already talked about. So we talked about motion, we talked about forces, we talked about energy, we talked about momentum. All of those things have a rotational component or like a rotational counterpart to them. So in some ways, rotation is really easy because it's just the same stuff we've been talking about, just now in a circle. But then there's like this other thing where like it's just like kind of just different enough that we need to talk about it separately. So we're just going to cruise through the rotational ideas and talk about how all of them are really just parallels of the things we've already, the concepts we've already talked about with, you know, momentum and energy and forces and motion. And I think I've got them in the order we went through the first time, which will be nice. So first, rotational kinematics. So a couple of just like general rotation things, and then we'll talk about analyzing rotational motion. All of the kinematics variables, displacement, velocity, acceleration, have a rotational counterpart. So for displacement, for example, we measure it usually if we're talking about it translational, which is just linear in a line, moving in a line. We usually use X or S. We talk about it in meters. If we're going in a circle, there's something called angular displacement or rotational displacement. We measure it in radians, and it's a theta. So it's the same idea. It's how the distance you've traveled, loosely, but if it's linear, it's linear displacement, it's X, and it's in meters. And if we're in a circle, we're measuring the degrees through which we're rotating, and we're measuring it, or the angle through which we're rotating it, and we're measuring it in radians. We can convert between all of these the same way. So we'll take whatever the translational or the linear value is, that's going to be equal to whatever the rotational value is multiplied by the radius of the circle that it's rotating around. So for displacement, the linear displacement is the radius times the angular displacement. Velocity, we've got angular velocity is omega here. Linear velocity is rotational velocity times the radius, and then we've got linear and angular acceleration. Angular acceleration we symbolize with an alpha, and we relate them the same way. The only one of these relationships that's on your equation sheet is V equals R times omega. But it's kind of nice because you've got this one, and you know that all of the other two function the same way, just with their own variables. So this is the rotational motion variables that we'll use in this section. We also have to talk about the right hand rule. So the right hand rule is used to determine the direction of a bunch of different velocity vectors. For right now, we'll talk about the angular velocity. But there's actually a bunch of different vectors that we can use the right hand rule for. And this is something that I feel like it's one of those things where if you get it, you get it. But if you're like, I don't know how to do it, it could be confusing. So I wanted to just talk about it for a second. The first step to using the right hand rule is to use your right hand. If you accidentally use your left hand, it's not going to work. You're going to mess up. So just use your right hand. And if you don't remember your right from your left, figure something out before tomorrow. I have a freckle on one of my hands, which I used for the longer than I should have as a child to determine my left from my right. Great. So you're going to use your right hand. After you do that, you're going to curl your fingers in the direction of the rotation. So this little guy up here is helping you figure it out. So this wheel, you can see the arrow here. This wheel is rotating like this. So the person's fingers are curved in the direction of the rotation. And then your thumb points in the direction of the angular velocity vector, or whatever vector you're looking for with the right hand rule. That's kind of like, we're talking about angular velocity, but this is kind of the general how you use the right hand rule for any of them. So curl your fingers in the direction of the rotation, and then your thumb points in the direction of the vector. So if we're looking at this cat on a Roomba here, the Roomba, I'm doing it. You can't see me, but I'm doing it as I'm talking to you. Hopefully you are too. I take my right hand. The Roomba is rotating. That looks to me like it's clockwise. So I'm rotating my hand, and my thumb looks like it's pointing down. So that's the direction of the angular velocity vector if I was in that room with that cat on that Roomba. Great. Rotational kinematics. So rotational kinematics functions the same way as linear kinematics does. And all you need to do is take the linear kinematics equations, plug in the rotational values. It functions the same way. For some reason, and I don't know why, only the first two rotational kinematics equations are on your equation sheet. I wanted to point out that the third one is also valid. It's just not on your equation sheet. But the other two are, and you just use them the same way that you would use the regular kinematics equations. You just have all of the rotational, like angular velocity, angular acceleration, instead of your linear counterparts. Okay, so now we're going to talk about uniform circular motion. And quite frankly, if there's one thing that I feel like is overlooked in this class that is important and on the test a lot, it is uniform circular motion. It pops up everywhere. It pops up because it's a version of simple harmonic motion. It pops up when we talk about gravity and orbits. It pops up kind of as its own thing too. So I wanted to just make sure that we spend some time unpacking UCM, uniform circular motion, so that way you feel confident tomorrow when you see problems that involve it. So first, what is it? Uniform circular motion is, by definition, when an object moves at a constant speed on a circular path. So what that means, what does that mean? Let's unpack that. The definition says constant speed. So the object moving in the circular path is moving at a constant speed. The magnitude is going to stay the same, but the direction is constantly changing because they're going in a circle, right? So speed is constant, velocity is not. And the velocity vector, as a rule, will always point tangent to the circle. So this is a great image here that shows you the velocity vector pointing tangent. If you can imagine, like, if maybe that's like a ball on a string rotating in a circle, if you imagine cutting that string, that ball is going to fly out of the circular path in a tangent line to what the circle was. For uniform circular motion, there is always a net force, there is always an acceleration, and we'll talk about that next. The net force and the acceleration in uniform circular motion is called centripetal force and centripetal acceleration. We'll talk about centripetal acceleration first. The object is accelerating. The centripetal acceleration is happening because of the change in direction, right? So the speed is staying the same. So the object's not getting faster or slower, but the direction is changing. We can calculate it using this formula, which is on your equation sheet. Centripetal acceleration is the linear or the translational speed squared over the radius of the circle, which is equal to the angular speed squared times the radius of the circle. That's centripetal acceleration. That centripetal acceleration is caused by centripetal force, the force that's causing the object to move in a circle. Now, this is something that I think is frequently not understood. Centripetal force is just a name that we give to all of the other forces we already know. It's just the thing making it go in a circle. There's not like a special extra centripetal force that happens in problems. It's just an extra special name that we give to forces like tension or friction or applied force or normal force. Whatever the force that is causing the object to move in a circle, that becomes the centripetal force. So there's not like, you're not looking at it and you're like, here's all these forces I know, and then also it's going in a circle, so it must have centripetal force. That's not how it works. You find the force that is like coming from something you know, whether it's a rope or a surface or someone's pushing it or whatever. And that other force that you already know about, we just give it that special name. We can solve for it using Newton's second law. And if we plug in the centripetal acceleration equation, we can solve for centripetal force. This one's not on your equation sheet, but it's a pretty easy jump, I hope, between your centripetal acceleration and then just plugging it into F equals ma. Okay, both the centripetal force and the centripetal acceleration vectors are pointing towards the center of the circle always. So if you're looking for what your centripetal force is, think about what force vector is pointing towards the center of the circle. That's what it's going to be. And I know there were some people in the discussion talking about how they didn't get to Unit 7. Here's another Unit 7 gravitation thing snuck in here. Anytime we see circular orbits are just uniform circular motion, with gravity being the centripetal force. So if you're like, we never learned that, I'm not sure. Again, it's like, this is not going to come up on the test very much. It's the smallest percentage, but kind of like the 2-second thing that I can give you here is that if you see circular orbit, treat it like everything you know about uniform circular motion. All rules apply. Gravity is your centripetal force. And then this rule is an important one that we're not going to talk too much about, but you've heard it now, so maybe you'll remember it. The velocity of an object in a circular orbit is independent of its mass. So if there's a satellite orbiting the Earth in a circular orbit, doesn't matter how massive it is, velocity is independent of mass. Okay, we're going to come back to simple harmonic motion also very quickly, because simple harmonic motion, or I'm sorry, uniform circular motion, UCM, is one more example of simple harmonic motion. So all of the simple harmonic motion stuff we've been kind of sprinkling in all the way through apply to uniform circular motion. This equation here, right, is the equation for simple harmonic motion. If we're talking about it in terms of circular motion, your x max is your radius, your angular frequency is your angular velocity. So those all work the same way. We just think about it slightly differently if we're talking about in a circle versus if we're talking about like a mass on a spring. We also can calculate period and frequency in uniform circular motion using this formula. We've already looked at it once. And this omega is your angular velocity. I like this picture too, remembering that if objects are going to have the same period, so they're going to rotate the same, have the same time for one rotation, then we have to increase the linear velocity in order for that to happen. So the green ball here is moving faster, linearly faster than the red one, because it's got more distance to travel in the same amount of time. Okay, and there's a lot of these here, so I'm gonna pick and choose which ones we do right now. Let's do this one. There was some requests for for simple harmonic motion. So this is a simple harmonic motion question. Got a particle moving in the xy plane. we've got coordinates given by, and we've got the formulas. A is 1.5 meters. Omega is 2 radians per second. What is the magnitude of the particle's acceleration? So this is a nice little simple harmonic motion combo with centripetal force and acceleration. So let me see if I can find this one to open up for you. There it is. Great. See if you can get an answer for that one. I'll give you a minute or so. Take another couple seconds. Okay, great. Let's take a look. So if we take a look, again, majority of you, great work. Correct answer here was E. And we'll talk about why. There were lots of you that responded to this one, and that's totally okay, but I'm wondering if we were confused. So I want to just talk through this one for a second. So I think, at least for me, when I first look at something and it's got cosines and sines in it, I'm like, oh gosh, do I have to take a derivative? What's the derivative of cosine? And you're just like, oh, gross. Never fear, you don't need to do any of that. These formulas are signaling to you that we're in simple harmonic motion, and all we need to do is pull out the values that we know from the formula. So we know that this 1.5 meters here, is the maximum displacement for the x, and when we're going in a circle, that value, this a value, is the radius by definition. Anytime you see this number in front of the cosine or the sine is going to be the radius. We also know that this number inside the parentheses in front of the t, in this case it's 2 radians per second, is the angular velocity, just by definition. So we don't actually have to do any sort of like, I see acceleration and I'm in position functions, and you're like, do I take the second derivative of the blah, blah, blah? No, unnecessary. All we need to do is pull out the radius and the angular velocity. The first thing that I did here is I converted the angular velocity to the translational velocity by multiplying the angular velocity by the radius. That's a formula that we know from our equation sheet. We get 3, and then I plugged in to my centripetal acceleration formula because I know that if we're moving in this uniform circular motion, then the acceleration has to be centripetal. So you do that, you get 6. The answer is E. Again, I'm going to skip. Let's do this one. So we've got maximum mass can be hung vertically from a string without breaking. The string is 10 kilograms. Length of the string is 2 meters long, used to rotate a 0.5 kilogram object in a circle on a frictionless table with the string horizontal. The maximum speed that the mass can attain under these conditions without the string breaking is most nearly. So you're looking for, again, centripetal force, uniform circular motion. This is not a simple harmonic motion question, I don't think. This is just like using the centripetal force and acceleration equations. Okay, the speed and contain this one. Okay, so take a minute or so and work on this one. Take another few seconds. I know there's a couple of calculations here, so it's going to take a second longer. Okay. All right, so for this problem, we're looking for the maximum speed without the string breaking. So if we take a look, how we figure it out, there's a couple of steps here, actually. Let me close the poll. Many of us are voting. Overall, again, y'all are ready. You're so ready. 70% of you got that right. That's so great. This one was a multi-step one and a lot to unpack. So if you got that one right, feel great. If you didn't, let's talk about it. No worries. So the max mass that the string can hold without breaking is 10 kilograms. So the first thing we need to figure out is how much is that in force. So all we'll do is realize that if it's hung vertically, then the force exerting on the string that would break it would be the weight. So we can know that the maximum force exerted on the string before it breaks is going to be the weight. So that's the mass of the 10 kilograms times 9.8 or 98 newtons. Again, if you used 10 for G and got 100 newtons here, great. That totally works. So from there, we know that that has to be the centripetal force, the maximum centripetal force that we can use before the string will break. So we'll plug that in for the centripetal force and we'll solve for the speed. When you do that, you get 19.79, which rounds to 20. So our answer is D. Great. So a couple of special cases to talk about. So sometimes you're going to see situations where you've got an object on a string and the path is going to be vertical. The centripetal force calculations get trickier when that happens because we have to take gravity into account. Same deal if you're talking about like a roller coaster and the centripetal force is the normal force, we have to take gravity into account. So we've got a couple of pictures here to help you visualize that. If the object's at the top of a motion, so centripetal force is pointed down, the gravity is going to add to whatever the other force is to find the total centripetal force. When the object's at the bottom, the gravity is going to subtract from the tension or the normal force or whatever to find the net force. So you'll see this typically swinging by a rope, a Ferris wheel, a roller coaster, something like that. Also curves. So this is definitely not worth our time in the last hour, but it is a picture here for you, which you can access in the slides after. There's two different types of curves you could see. You could see an unbanked curve or a banked curve. Unbanked curves means the road is flat and you're just turning. When that happens, static friction is the thing that provides the centripetal force. I feel like that one, if someone doesn't say it to you, it's like, I don't know, you're just turning. I don't know what the force is, and it's the static friction that's causing the centripetal force. And then for banked curves, it gets complicated, but we know that the horizontal component of the normal force is going to cause the centripetal force. Static friction also might contribute if it's present. So take a look at these pictures in more detail later tonight, maybe. But if you've got time, this is definitely not your highest priority. But if you're interested and want to take a look, we've got some nice force diagrams here for you. Okay, moving on. Torque and rotational inertia. So we talked about motion and its rotational counterpart. Now we're going to talk about forces, their rotational counterpart, which is torque. So what is it? Torque is the force that causes an object to turn, and there's two things that affect it: the force that's applied and something called the lever arm. The lever arm is the distance between the point of the force's application and the axis over which it's rotating. We've got a formula for it. The torque, that's tau, that's the Greek letter T. Greek letter T stands for torque. It's going to be equal to this R, which is the lever arm, cross the force. So this is a cross product, which is different than the dot products that we've seen before. But I warned you, or I told you at the beginning on the equation sheet, you've got that kind of cheat sheet. You've got that cheat sheet at the end of your equation sheet that tells you what to do if you see a cross product. It's also here for you. So to figure out the magnitude, if you've got a cross product, you're going to do RF, or the two things, and you're going to multiply by the sine of the angle between them. To find the direction, you're going to use the right-hand rule like we talked about earlier. So you'll rotate your fingers in the direction of the rotation, and your thumb will point in the direction of the torque. There's also positive torque and negative torque. So I put this picture in here. I know that y'all never use analog clocks very often anymore. And so clockwise and counterclockwise is actually kind of hard, which I totally get. So I wanted to just put a picture here for you. Clockwise is in this direction, counterclockwise in this direction. And then positive torque is counterclockwise, negative torque is clockwise. Okay, so let's talk about rotational inertia. Rotational inertia, moment of inertia, those are the same thing. And it's a measure of an object's resistance to rotational acceleration. So it effectively acts like, if we're thinking Newton's second law, just like in linear, you've got F equals ma. Rotational inertia acts like the m, but we're going in a circle, right? And it doesn't just depend on how much mass it has, but it also depends on the distribution of that mass. So if the mass is close to the axis of rotation, it's easier to rotate, so it's a smaller rotational inertia. If the mass is further, there's more rotational inertia. We have a formula here to calculate it. If it's something that's got discrete like particles, you would just sum up the mass of each of the particles times r squared. If it's like an object that you have to find the rotational inertia for, you would integrate r squared dm, like here. Linear mass density is another thing. I think I saw it earlier in the chat. It's kind of a weird one-off thing, and it's not on your equation sheet, so I did throw it on here for you. It's defined as the amount of mass per unit length. So if there's a small chance that this comes up on the test, and if it does, if you don't know this, you're kind of a little bit, it's a little challenging. So maybe memorize this. All it is the amount of mass per unit length, so dm dx, and we'll see it in rotational inertia center of mass calculations. Okay, this is important. So with rotational inertia, we've got the parallel axis theorem. This is something that is not on your equation sheet, but you should memorize it. I think Kristen threw that in the discussion earlier. And what it allows us to do is to find the rotational inertia around any axis parallel, hence the name, to the center of mass. So if we know the rotational inertia through the center of mass, we can find the rotational inertia around any other axis that's parallel to it. And all we have to do is take the rotational inertia around the center of mass, add in the mass times the distance between those two axes squared. So this is the parallel axis theorem. you should definitely memorize it. It probably will pop up if you haven't seen it before. It's super easy to use. We just have to know that it exists first of all, and then what it is second, right? So definitely add that one to your list of things to remember. So let's do a practice here. This is a parallel axis question. We've got this uniform rod. We know the moment of inertia through its center, and it's asking about the moment of inertia through point P, which is halfway between the center and the end of the rod. So let me open up a poll here. Let me find it. Take a second and work on that one. Take another couple seconds to work on this one. Great. Last chance if you're going to vote. Awesome. Okay. Overall, y'all, your brains are so strong. We've been at this for a long time and you're still getting them right. So good work. Correct answer here is E. 71% of us got it. Let's talk about it. So we know the rotational inertia around the center of mass is 1/12 ml squared. And we know that the distance between the center and the one that they're asking us about is L/4. So all I'm going to do is use the parallel axis theorem. And this is how I do it. I plug in the rotational inertia around the center of mass. And then we know that we just have to add m times the distance between them squared. So we don't know what m is, but we know that it's m. So we're going to plug in m. And then the distance between them is L/4. We're going to square. Remember, when we square a fraction, we have to square the top and the bottom. And then do this weird simplification thing. So this is a super weird fraction, but it is the correct answer. 7/48 ml squared. Okay, awesome. So related to torque here and putting together torque and rotational inertia is going to be rotational statics and dynamics, which is basically like forces but rotating. And so all of the same kind of principles apply. So the first thing we can talk about is rotational equilibrium. So just like in regular equilibrium or like linear equilibrium, when the net force is 0, the object's in equilibrium, same deal, but now we're kind of adding this extra rotational wrinkle. So rotational equilibrium occurs when the net torque is kind of like our force, but in a circle, right? Torque is 0. And then now we can actually complexify, I don't even know if that's a word, our static and dynamic equilibrium definitions, because static equilibrium is now true when both the net force and the net torque is 0 and the object's at rest. And then dynamic, net force and net torque is 0. Object is moving with a constant linear and angular velocity. So we've got this Newton's second law of rotation that we can use. And it functions just like you would for the linear one. It's just, again, rotating. We've got the sum of the torques, because torque is our force in a circle, and it's equal to the rotational inertia times the angular acceleration. Looks like this on your equation sheet. Hopefully you can see how it looks just like the linear one. It just uses our angular values. Rotational energy is another big idea here, and it also functions just like the linear one, but we're in a circle. So we've got this idea of rotational kinetic energy. Rotational kinetic energy functions just like, you treat it just like linear does, except for we use our rotation values. So instead of 1/2 mv squared, we've got 1/2 I for our rotational inertia, and then omega for our angular velocity squared. I know I'm cruising fast, but this is all just like it. My message here is like, it's the same thing. It's just in a circle over and over and over. Conservation of energy, same thing. But now if we add in the circle, we have to also take into account the rotational kinetic energy in our total energy. So we're not going to do this one. I'm not going to have you do this one, but I am going to go through it because I do frequently think we see something like this, and I want to make sure you've seen it. So we've got this uniform solid cylinder rolling without slipping. So rolling without slipping is a big cue that you're going to see. And when it says rolling without slipping, it's telling you that it's the slipping part. What we care about is the linear kinetic energy, the rotational kinetic energy, and then the potential energy. And so we're going to roll without slip down this 1 meter inclined plane, and then it's going to launch onto the floor between a distance d. It tells us that there's no frictional energy losses, tells us the rotational energy of the cylinder. So A says calculate the total kinetic energy of the cylinder as it reaches the horizontal table. So in order to figure that out, we're going to use conservation of energy. We can find our initial potential energy at the top here. That's what I do right here. And then we know that that's going to be equal to the total kinetic energy at the bottom. So all we need to do is plug in our mgh and solve for our kinetic energy at the bottom. And now here, calculate the angular velocity of the cylinder around its axis at the moment it reaches the floor. This is the one that I really wanted to make sure that we looked at because this is kind of weird. Or it's not weird, but it's just like we have to just like, there's like some substitutions that are non-obvious that I want to show you. We need to use this linear speed equals the radius times the angular speed, or angular velocity and linear velocity in this problem. And this little tiny equation here helps us a ton in any of this rotational stuff. And so this is one not to sleep on. We use it all the time. So anyway, in order to find the angular velocity, we're going to use our kinetic energy. And we know that the kinetic energy, the total kinetic energy, has to be equal to the translational or the linear kinetic energy plus the rotational kinetic energy. So I will walk through this math a little bit. I know that breaks my rule all afternoon, but I think it's important because there's some substitution going on. So first thing I did is I plugged in my linear equation and my rotational equation for my kinetic energies. And then we know that we need to get to angular velocity, and we know that we don't know anything about the linear velocity, so I need to get rid of it. So I plugged in my angular velocity here for my linear velocity. And then just as I was going along, I also plugged in my rotational inertia equation from the problem. From here, solved, plugged in some numbers from the problem, got an answer for the angular velocity. So rolling without slipping, let's talk about it more. Objects that move with both linear motion and rotational motion are this rolling without slipping. And the torque that's causing the rolling comes from the static friction. So if it says rolling without slipping, there's friction. You just know that. But it's static friction in that like every instant the ball is rolling, the static friction of the surface is the thing that's causing the torque that's making it roll. So this is a nice little picture here. Talking about the different types of velocities happening if we're moving without rolling, if we're just rotating or just rolling, and then if you're moving both linearly and rotating at the same time here. So there's a couple of tips here for anytime we see rolling without slipping. First one is, like I just said, converting between the linear velocity and the angular velocity is going to just be huge. Being able to bounce back and forth depending on what you're looking for is going to be super helpful. So make sure that we don't sleep on this V equals R omega formula. When we see rolling without slipping, it should cue you to use either Newton's second law and or conservation of energy. And I always say, try energy first. Energy usually simplifies the problem. So if you can, try energy. And if you can't use energy, then shift over to like forces or kinematics or things like that. Okay. I think we're going to skip this guy too, just as a matter of time. So that way we can talk about angular momentum. Great. So angular momentum is the last, I think this is the last big rotation topic. And it's an important one. So we kind of went through rotation and we talked about the motion parts of rotation, the force equivalents for rotation, the energy equivalents for rotation, and now we're talking momentum. So angular momentum, symbolize it with a capital L, and it's a vector describing how difficult it is to stop a rotating object. So it's just like linear momentum, but again, in a circle. And there's two ways to find it. We can find the angular momentum using the position vector and the linear momentum. You can see that here in this picture on the right. If we were to use that right-hand rule, we could see that the vector points up. Alternatively, we can use the formula down here, which is the rotational inertia times the angular velocity to find the angular momentum. In your equation sheet, it looks like this. It's R cross P, or I times the angular velocity, I omega. Okay, so this is another cross product, right? So as another reminder, we would just multiply the two, take the sign of the angle between them to get the magnitude, and then use the right-hand rule to get the direction. Okay, so there's another comp between force and linear momentum, and then torque and angular momentum. So we remember from, who knows, maybe an hour ago, that the force acting is going to be equal to the derivative of the momentum with respect to time. That's like that's how we get to impulse momentum, right? We also know that if we're going in a circle, then torque is kind of like force and angular momentum is kind of like linear momentum. So there's also this relationship between torque and the derivative of the angular momentum with respect to time. This is not on your equation sheet. This guy is. So if you just remember that there's also a rotational component to it, great. Or if you wanted to, you could memorize it tonight. So why do we care about conservation of angular momentum? Well, there's a couple of implications here that you could possibly see on your test. And like, it's super important in life, obviously, but we're talking about the test, right? So in an isolated system, add angular momentum to the list of things that are conserved. And remembering that in an isolated system, that's no net force, no net torque. This is a great example of an implication of it. So you've got this guy, he's got weights. His rotational inertia to start is big, and he moves with a smaller angular velocity. When he brings the weights in closer to his body, he decreases his rotational inertia. Because angular momentum is conserved, his angular velocity has to increase. So you can see he gets fast, he starts spinning faster because that angular momentum has to be conserved. This is also how this works for ice skaters, right? So if you've ever seen like a ice skating something, the Olympics are coming, even though I know it's the Summer Olympics. When ice skaters twirl like this, they typically start with their arms and sometimes even a leg out, far away from their body. And they twirl and they go kind of slow. They do this cool thing where as they bring in their arms, they start to twirl faster. And the reason for it is the conservation of angular momentum. As you decrease your rotational inertia, you increase your angular velocity. This also has implications in gravitation. So this is another sprinkling of Unit 7 right now. this is an important implication of conservation of angular momentum in orbits. And there's a lot kind of like that goes into this, but the takeaway is this formula down here. So if you don't have this written down somewhere, this would be a great time to write that down and just remember it. This is not on your equation sheet. We can relate the velocity and the radius at any one point in the orbit to any other point in the orbit by this relationship. So if we multiply the velocity and the radius of the object in orbit together, it's going to be equal to the velocity times the radius of the object in orbit at any other point. And this has to do with this comes from angular momentum conservation. Okay, let's do a practice. So we've got a star, mass is m, radius is r, rotating with an angular velocity of omega. After the star collapses, it's got the same mass but a smaller radius. Which of the following statements below is true? So let me open up a poll here. This is another one of those conceptual questions we're practicing. Great. Take a second and see what you get for that one. Okay, take another couple seconds if you're going to vote. All right. Okay, so let's take a look at this one. Overall, we got the right answer. The correct answer here was D. And like I said, overall, y'all did well, but it's not quite as unanimous as I'd like. So let's definitely take a look and talk about it. One thing to take away here between regular momentum and angular momentum is that if you're not sure, if there's a problem like this on the test and you're like, I don't really know, I'm not sure, if there's one that says the momentum is conserved, your default is that one is correct, because pretty much always, I'm not gonna say always, but pretty much always, angular momentum and linear momentum are both conserved. So like, if you're trying to eliminate some, or if we're at a point where you're kind of guessing or you're short on time or whatever it is, go with the one where the momentum is conserved. Let's talk about why, though, specifically in this problem. So we know that angular momentum is conserved. So right away, that should rule out B and C, because B and C says that the angular momentum gets bigger, and that can't happen. That doesn't happen. So now we have to think about what's happening with the rotational inertia and the angular velocity. So if angular momentum is conserved, then we know that the relationship between I and angular velocity, they're like inverse of each other, right? So if I goes up, omega goes down. If I goes down, omega goes up. In the problem, it says that the star collapses, same mass, but a much smaller radius. So the mass is getting closer to the axis of rotation. So the I gets smaller. Rotational inertia gets smaller. So the angular velocity has to get bigger. So A can't be true. Angular velocity has to get bigger. Now, so we're down to D and E here. And so the question is really, does the rotational kinetic energy get bigger or does it get smaller? And if we think about it in terms of the formula, we know that rotational kinetic energy is 1/2 I omega squared. If omega is getting bigger and omega is squared in this formula, K also gets bigger. So our answer here is D. Okay, so to summarize for rotation, basically, if you're looking at this chart, your takeaway is everything that we do in the translational or the linear world pretty much has an angular rotational counterpart, and they function the same way. So you've got your motion values here. They've got their angular components. We know that mass is kind of like moment of inertia or rotational inertia. Force is kind of like torque. And then we've got Newton's second law. We've got rotational kinetic energy. We've got angular momentum. So all of the things that we do in the linear world have their rotational components. And if your default tomorrow, if you're like rotation, I don't know, default is treat it the same way that you did before with the linear stuff and just hope for the best. And I say that like kind of tongue in cheek, but honestly, so much of it works the exact same way that if you need to just make a choice on the test tomorrow, that's what you go with. So we're going to skip this one just because I want to make sure that we get to the tips and tricks. These slides are here though. So if you want after this to pull up this slide, time yourself, put 15 minutes on your phone, and then go through and score it. It is here for you. This was the last one we were going to do, but I think I want to just, again, be respectful of the fact that we want to make sure we get to the tips and tricks. So we're going to take one more break. So take 5 minutes to really just stretch and breathe and get one more snack, one more power snack. I'm going to go get an Oreo, I think. And then we'll come back, we'll do tips and tricks, and then send you on your way. So it is, in my world, it's 4:22. So we're at 22, whatever hour it is. We'll come back at 27. Alrighty, folks, let me know that you're back. We'll do a couple more would you rathers just to come all back together, and then we'll do tips and tricks. So here's the first one. Transitioning from food to tech. Would you rather always have the newest technology or the best food in the world? I have a very strong answer to this one. So take a second and take a vote. What do you think? Very curious what y'all say. Take another couple seconds if you're going to vote. Great, 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 great. Okay, so we're pretty split on this one too, although I will show you. There we go. So most of us say best food, although we are pretty split. I think I land in that best food too. My iPhone is also really old, so newest tech maybe is not for me. Okay, great. So in this last half an hour, we are so close, y'all. You are hanging in there, and it's awesome. So in this last half an hour, we're just going to hit some final tips and tricks, things to take away as you finish up your studying tonight and get ready to absolutely crush the test tomorrow. So we'll talk about multiple choice first, and then we'll talk about free response, and then we'll just do a little bit of a wrap up. So first, for multiple choice, let's just talk about the goal and kind of like what to expect. So you've seen some examples of multiple choice through this 4.5 hours. And most of those examples were pulled from old versions of the test, so you kind of get a feel for what it is. But the main goal of multiple choice is to test kind of your overall knowledge of mechanics. So any of the calculations that you'll be asked to do are going to be kind of quick. You'll be asked to just like apply a formula or like maybe put two together quickly. If it's taking you a long time to do a calculation, I would say take another look. You're probably doing something. You could get to a correct answer, but there's probably a faster way for you to do it. Remembering again that energy is typically faster than kinematics. So it's taking a long time, take another look, but generally multiple choice is going to be quicker calculations. It's going to be interpreting graphs. So we've seen a couple of graphs today, and they'll give you a graph and you've got to do something with it. And then lots of conceptual questions. So we've seen a bunch of those today. Any of those I just remember I went on that just say momentum's conserved ramble a couple minutes ago. Any of those this gets bigger, this gets smaller, this is conserved, this is not conserved. Conceptual questions, anything about Newton's second law, conservation of energy, momentum, and then XY independence is also a big concept that comes up a lot in the multiple choice section. As far as there's these things that if you are taking this class like in school, your teacher might have talked about them, they might not have. And if you aren't taking this class in school and you're self-studying, you definitely probably have not seen this. But there's different types of questions that you expect for the multiple choice. And there's 7 science practices that go with the test that are listed here. I put these up here just to point out that the biggest sections that you'll see are going to be these theoretical relationships. So that's the formula work and the concepts, really the concepts, and then the mathematical routines is the formula work. So when you're looking at multiple choice, those are the big ones that you are being asked for. Overall tips for multiple choice. So first one, because some of these are going to be for both, but I'll say them twice. Know the equation sheet. So we have looked at the equation sheet a couple of times today. We'll look at it one more time in our wrap up. Just know where things are. Again, you don't need to spend all night memorizing equations, but it is helpful to know where to look on the equation sheet for what you're looking for. Another helpful tip here is to just make sure that you read the question all the way to the end. Sometimes I pointed this out kind of early in one of the earliest questions. Sometimes they sneak really important information right at the very end of the question. So read the question fully, pull out all of the info that you're given first. If it's a lot of numbers and stuff, make one of those lists that I've been showing you with like M equals 2 kilograms and V equals 3 meters per second or whatever else, right? Make a list, write down what you know. It should take you about a minute to solve each problem. If it's taking a lot longer, there may be a faster way. I've said that. You've got 35 problems in 45 minutes, so you can do the math there. I think it's like 75 seconds a problem. When you get to your multiple choice section and you open it up, the first thing that I recommend that you do is to skim over the whole section and do the ones that you know first. There's a couple of reasons. First one for doing that is to just like, you got to get some momentum, no pun intended, going, right? Like you got to just like get a couple questions in the bank. You got to start by feeling good, find a couple that you know and start there. Also timing, right? You want to be able to do the ones that you know first, that way you know how much time you've got left to figure out the ones that you have to think about. So you definitely do not need to go in order. And in fact, you probably shouldn't go in order unless you're just like cruising, I guess. But you definitely don't need to go in order for the multiple choice. Do the ones that you know first. Next tip, process of elimination. So as you're looking at these questions, there's going to be some things, whether it's like a concept question that says some physics that you know is not true, or it's a numbers question and one of the numbers is like way out there and you know is not true. Use process of elimination. Cross those ones out. Those don't make sense, right? That way, if you end up having to take a guess, you're at least improving your odds. Another tip, make sure to use 10 for G. 9.8 is great, but especially in the multiple choice when you're just looking to pick a letter, 9.8 or using 10 is going to simplify your calculations. And you can even probably do more of them in your head than having to pull out the calculator. And you can still get an answer that's going to be close enough to know which letter to pick. So use 10 for G. Totally great. Definitely not going to be penalized for that. And then the last one for the multiple choice is just don't leave any questions blank. You do not get penalized for guessing. As you're getting close to the end of the time, even if you have to just randomly fill in bubbles, hopefully we're not there, but if we are, definitely at least fill in a letter because you don't get penalized for guessing. So don't leave any questions blank. Okay, so now let's talk about free response. Free response is I feel like the more intimidating one for a lot of people, right? So I want to spend a little bit of extra time both going through some tips and tricks, but then also kind of unpacking what to expect in the free response section. So if multiple choice's goal is to test like how much kind of like how many different physics topics you know about, and the more like general breadth of knowledge, free response is testing depth. So it's going to be just like a couple of topics per question, and it's going to ask you lots about it, right? And you've done a couple of these practice problems in this CRAM, so you kind of get a feel for what it's asking you, right? It asks you to like really get into the physics. They're going to have multiple parts. It's going to combine topics from different units together into one situation, and there is partial credit. That if there's one thing you're taking away from this part of everything is that with the free response, there's partial credit. You definitely should go for it. There's different types of questions you can see. There's always by rule, there's one experiment question. So it either will like give you experimental data that you have to work with or ask you to design an experiment. But there's always one experiment question. Frequently, you'll see something that's a derivation. So that will be like, sometimes it's like rotational inertia. Sometimes it's like derive an expression for the velocity of something using these variables. But it's more of a like using letters in algebra and less plugging in numbers for the derivation questions. You'll frequently see a comparison question or two. So we did one of those in that second free response practice that you did, talking about, what happens if we change the situation a little bit. Do things get bigger? Do they get smaller? Do they stay the same? What happens qualitatively or conceptually to the values. And then questions that I just call like, do you know your stuff, right? Like, can you write a net force equation? Do you know the forces that are happening? Can you find the angular velocity of something with rolling without slipping? You know, just like here's some physics. This is like some important physics. Do you know how to do it? Yeah. So for the science practices, again, it's here. Maybe you've seen them, maybe you haven't. The big ones are still theoretical relationships and mathematical routines. But there's this representing data and phenomena that bumps for free response, and that has to do with the experiment question, typically. So now the task words. So we're going to spend a couple of minutes unpacking the task words. And what I mean by task words is when you're looking at the free response problems, they're going to give you a direction. They're going to tell you what to do. And depending on what word they use, you have to do like different levels of complication with it. Now, do I think that it's worth you spending the rest of your night trying to memorize these different task words? No, probably not. But it is helpful to at least recognize, I'm going to pull out a couple specifically here because it might save you time if you happen to remember when you take the test what these are. So there's 2 slides of this, just to warn you, and we're not going to like dig into every single one of them right now. I did that actually in the free response tips and tricks CRAM if you want to go back, but I'm going to pull out the ones that I think are most important to talk about in the last couple of minutes here. So first one that I think is maybe not as obvious, but just needs to make sure that we talk about is determine here. So when it says determine, it's super vague, and that's actually helpful for you a lot of the times because it's not telling you that you have to use math, or it's not telling you that you have to write a paragraph. You can figure out the answer, come to some sort of conclusion, however you want, whatever gets you there. But it kind of is like more vague on purpose, so that way you can do whatever comes to you, both like in your brain, knowing how to do it, but then also whatever would be fastest, right? So determine is one that I wanted to point out. Calculate is another one here. I know I'm going up the list, but calculate is perhaps obvious because I think it implies that you want to use numbers, but this is kind of the most, I think this is the most rigorous of the directions in terms of like the number side, right? So you need to come up with a number as an answer, needs to have units on it. You need to vaguely be aware of significant figures. It doesn't have to be perfect, but you know, it shouldn't have like 20 decimal places or 20 numbers after the decimal. And be kind of rigorous if you see calculate. What else? Estimate is another one. Estimate, a lot of times you'll see estimate in the experiment question, especially if they give you a graph and there's some data points that are not super explicitly obvious what the numbers are. So estimate is just kind of like exactly what it sounds like. Roughly calculate it, right? Give like a general educated interpretation of the experimental evidence that you're looking for. Okay, second page here, justify. So justify is kind of a weird one. So just when they say justify, typically they're going to give you some sort of conclusion. So whether that is like a rotational inertia, I keep coming back to rotational inertia, but whether they give you like a formula or they give you just like some conclusion in words, you have to go in and explain why that's correct. So you're gonna do some math or do some or you could write how there's evidence in the problem that supports or qualifies the claim that is provided. A big one, and I'm gonna pause and take a deep breath here because this is if there's one that you're taking away right now, it's this one, this thing that I'm about to tell you. The difference between plot and sketch. So this is going to save you a lot of time if we get lucky and it tells you to sketch instead of plot. So when the test tells you to plot something on a graph, you have to be super thorough. So you need to put your data points on, you need to put a scale on each axis, you need to label that axis with units and what it is, and it has to be consistent if there's more than one graph. So that one you've got to be like I'm picture just like head really close to the paper, measuring it out, plotting your points, have to be really, really precise. If you see sketch or draw, you don't. So don't plot unless you have to plot. If it says sketch or draw, that's a looser expectation, and use it to your advantage. So if we see sketch or draw, all we need to do is kind of like generally show the shape, especially if it's a graph, generally show the shape of the graph, but making sure that if there's more than one graph, you do have to be consistent between the different types of graphs. So we looked at one, I think, earlier in the CRAM where it was like a velocity graph and then a position graph. They have to be consistent with each other, right? So like if the derivative of your position graph would be like a linear slope of +2 or whatever, just make sure that the velocity graph then has a line that's a linear line that's, we're getting to the end and my brain is stopping, a line that's got a slope of +2-ish, right? So making sure they're consistent, but the difference between plot and sketch, plot, you have to actually like go in and label your axes and make a scale and plot your points. Sketch is much more loose. Just draw the shape and make sure that kind of like the main relationships between the different graphs go together. Okay. If it says verify, that's the other one I wanted to pull out. If it says verify, that's kind of like justify, except for you kind of have to connect the dots in between them. So you sometimes I see verify if it's like verify that it's an elastic collision, for example. If you see verify that it's an elastic collision, you're like, oh, kinetic energy is conserved. So I need to make sure that the kinetic energy before the collision and the kinetic energy after the collision are the same. That would be a verify. You can also use like the data if they give you that for verify. Okay, so let's go over a bunch of tips for the free response. So you're going to get there, you're going to do the multiple choice first, and then you're going to be done with that, and it's going to be time for the free response. And we would just need to make sure that we are maximizing our efficiency and our time as we go through, so that way you can show all of the awesome studying that you've done and physics that you know. So again, first on this list always is just going to be know the equation sheet, right? So just know where it is. Again, you don't need to memorize it. I know I keep saying it. You don't need to memorize the whole thing, but you really, really, really don't want to be wasting time searching through 3 pages of formulas to find what you're looking for. So know where it is, even if you don't know what it is. I do have on here, it's good to memorize the most used formulas. I'm hopeful that at this point, like Newton's second law, hopefully you know that one by now, but only if you have time. I also, like, if we're prioritizing for the rest of tonight, definitely memorizing the formulas is not your priority, as long as you know where they are on the equation sheet. Similar to the multiple choice, when you get your free response, first thing you're going to want to do, skim through the whole thing first, and then start with the question that you feel the most confident in. You want to start with some confidence, you want to start with some momentum, you want to kind of get some numbers and some words on the paper early. So start with whatever question you feel best about. And you can definitely bounce between them, right? You have the 45 minutes to do all 3. Doesn't matter what order, or if you do one then the other and come back. Bounce around as you need to. Ideally, each question should take you about 15 minutes. That obviously, you're not, I was timing you 15 minutes earlier, but you have 45 for all 3, so you can play with that as you need to. Hopefully you've got one that maybe takes you a little bit less, and then one that takes you maybe a little bit more, and then you finish on time. Another really big takeaway here is to show your work. So I am not sure that everyone knows this, so I want to make sure that I say it to you all. The people that grade these tests are teachers. Teachers get together and they grade, physics teachers, like AP teachers, are the ones that get together and grade these tests. So the teachers are really, really, really looking for any reason to give you some points. So show your work. The more that you give to them, the more likely they are to be able to give you a few points. We saw examples today in the free response about how like even just writing down the law of conservation of energy and like the initial energy at the beginning, or the initial for momentum, the initial momentum at the beginning is equal to the final momentum. That got points, right? Just writing that down got points. So show your work, write down what you know. That said, you can't, unfortunately, you can't just like write down the whole equation sheet and wish, right? Like you do need to, they're not going to be okay with it if you just write down every single formula that you possibly know. But even if you have like some inkling or any sort of guess, write something down so that way you're at least given maybe a couple of points. Next one, know the task words. We just went over those. Feel free, you have access to these slides, go back to them, read them over. Don't do more than you have to based on the task. And then if they give you a graph, you need it. Like if they're not just giving you a graph, you're going to use it, right? So make sure that if you have a graph in one of these problems or two of these problems, use the graph. Okay, next. One good strategy as you're looking at a problem is as you're reading it, make a list of what info the question is giving to you. So whether that's like on the side or you want to underline or circle or something like that, make a list of all of the info the question gives you so that way you don't have to keep going in and rereading all the words, but you have a list as a reference for everything that you know. That will make it easier to find whatever it's like the topic or the equation or whatever you're doing, it will make it easier to find what you need. So read it over once and then make a list of everything that you're given in the problem and then use your list. That way you aren't like swimming in words. Okay, and this is similar to when I said show your work, but again, there's partial credit, right? So write down something, write down a formula, write down a thought, write down a random, like, I think it might be this, even if you have no clue, write at least some of it. And then this is also something that I think not everyone knows that they can do that's like allowed. If you don't know the answer to the question in A, make up a number, call it 10, I don't know, make up a number and be like, okay, well, in A, maybe the force is 10 newtons, and then use that 10 newtons in the rest of the problem if you know how to answer the rest of it. So you won't get points for part A if you don't know how to do it, but that way you can use it to get points for the rest of the problem. So just because you don't know A doesn't mean that you're just like out of luck. You can still, if you know the rest of the problem, you can still answer the rest of the problem. Just make up a number for the stuff that you don't know. And then if you know how to use that number and the rest of the problem, do it. Okay, next one, include units in all of your answers. Sometimes you get a point for just having the units. So just like as you're finishing up, as there's just a couple minutes left, go back through your answers one more time, make sure they all have units. If you don't know the answer, another thing regarding units is that you can use them to your advantage. So if you have no clue how to solve something, but you do know, like, you've got a velocity maybe, and you've got a time, and you've got force or whatever, see if you can't get the units to cancel out into the unit of the thing that you're looking for by like multiplying and dividing and adding and subtracting. So sometimes using them to figure it out is helpful, or checking your work that way too is helpful. Next one, leave algebra heavy answers for last. So we talked about this, I think, in an earlier free response, but if you're working and you've got a lot of the tests left and you're like, okay, well, this is going to take me a minute to do all of this algebra, leave it. Just get it set up so you're like, all I have to do is do the algebra to get to an answer. Leave it there, do the rest of the test, and then come back and do the algebra when you're just like at the end. because what you don't want to do is spend so much time working on the algebra that you leave other answers blank because you're so busy trying to get the answer for the algebra question, right? Definitely leave those for last. Next, this is oddly specific, but it is important. And I think I saw a question in the discussion earlier about it. If you're specifically asked to draw a free body diagram, don't draw components on it. You actually will lose points. If you need components to solve it, like if you need it for yourself, make a second one on the side for you. But on the official one, don't draw components on the free body diagrams. They usually explicitly say, do not draw the components, but I am also saying it to you. Don't draw the components, you will lose points. And then I think lastly, write legibly and just like be super obvious about your answers. Again, these are like real teachers, real people grading your free response. So make it really obvious what your answer is. Be really, intentional about showing your work and your steps, and obviously not, make sure you finish, but if you have time, the more you can telegraph your answers and make it easier to give you points, the better off you'll be. Okay, so let's revisit the equation sheet one more time now that we've done all of this, and just like check mark about all of the things that we've learned. So I'm going to switch my screen one more time. You're going to see me. I'm a little more haggled than I was a couple hours ago because we've been here for a while. But let's look at it. Okay, so if we take a look at these formulas, we talked about the first three. Those are the kinematics equations. Next one, Newton's second law. Check, did that. Next one, relationship between force and momentum. Check, did that. Next one, impulse momentum. Check. Next one is just straight up momentum. Check. This one here, this is friction, right? We talked about how we treat it slightly differently if we're doing static versus kinetic, but generally, this is the friction formula. Check, talked about that. Next one, change in energy and work. So this is the work energy theorem right here. Talked about that. Great. Next one here, this is straight up linear kinetic energy, right? 1/2 mv squared. Linear kinetic energy. The next two are power. So I talked about that for exactly 30 seconds, if you remember. You might see it on there for like a question, but there's two formulas for it. I feel like it's taking up more space than it deserves on this formula sheet personally, but it's fine. Next one, gravitational potential energy close to the surface. Talked about that. Next one, centripetal acceleration. Remember that we have the linear and the angular velocities. Talked about that. Next one is torque here, right? This is torque. This next one is Newton's second law, rotation, right here. This is moment of inertia or rotational inertia, how we calculate it. I think this next one is the only one we didn't talk about today. This is our center of mass equation. So if we need to find the center of mass of a system, we take the mass of each of the objects times the distance from the center, add them up, divided by the sum of the masses. This one, remember this one's so important, linear and angular velocity, the relationship between small but mighty. This next one, angular momentum, rotational kinetic energy, rotational kinematics. And then in the second column, Hooke's law, this is spring force, right? Restoring force, spring, potential energy. This next one is our simple harmonic motion equation. Remember that x max is either the radius or the amplitude of the motion, the furthest point away, and omega is the angular frequency or the angular velocity. We've got 3 period equations. We've got universal gravitation, and then we've got potential energy for universal gravitation or for like big objects, right? I totally blanked. I had them all, and then I blanked on the last one. How sad. So this is if we're talking about the potential energy between big objects with masses. Great. So we talked about everything except for one. Y'all are so ready. Let's just do a couple final wrap-up things, and then I'm gonna send you on your way, and it's gonna be awesome. So let me switch back to my slides just one more time. Okay, so in these last couple minutes, generally, when you're looking at a problem, tomorrow, here are some questions you're going to ask yourself. First, what's the object doing? What's it doing? Draw a picture if you need to. Next, what direction is it moving in? Is it moving in one direction or is it moving in two directions? If it's moving in two directions, we need to find our x and our y components first. Next question, is it moving at a constant velocity or is it accelerating? If it's accelerating, what's causing it to accelerate? That's going to lead us towards forces. Lastly, we talked about the big four today, right? We talked about motion, we talked about force, we talked about energy, we talked about momentum. What type of problem is it? Is it motion, force, energy, momentum? Sometimes it could be more than one, but what way do you want to solve the problem? And then as our like little wrinkle, is there rotation involved? If there's rotation, remember we have to do everything, but just kind of like twice, talk about the circular part too. And I've said this a bunch of times, but generally you want to use energy to solve the problem first. If you can't use energy, then shift over to force and kinematics. So today, for the rest of today, a couple of things. Make sure that you go to bed early tonight. Trust that if you're still here with me, man, you've done everything you can do. It's time. You're ready. Go to bed early. And then before you go to bed, make sure that you have your materials set out so that way you're not in a panic in the morning. I know I sound like everyone's parents or grandparents or whoever your people are right now, but have it all set out. Know where your calculator is. Make sure that it has good batteries in it. That would be tragic if you were there and then your batteries ran out, right? So make sure you've got a calculator with good batteries and you've got some pencils and you have everything set out before you leave. Tomorrow, make sure that you eat a good breakfast. Don't eat anything new. No upset stomachs. That's not going to help. So eat a good breakfast. And then finally, just like take a deep breath, right? Because remember that it's ultimately just one test. It will be nice to pass. And if you're here with me, then you've been working super hard and you're working towards it. But it does not determine your worth as a human. So just kind of the more that we can keep that perspective, hopefully the calmer we can be tomorrow and the more likely it is we'll do well, right? So just when you're stuck tomorrow, because you're going to get stuck, everyone's going to get stuck at one point or another on that test tomorrow. When you're stuck, take a deep breath, just list what you know, what you're looking for, draw a picture if you need to, and then just trust what you know. You're here. We've been here, right? You've got this. Upcoming event. Yes. So the last slide I always do is upcoming events here. And yeah, I mean, there's only one and you got it. And I'm so excited for you. So if you would like to keep this conversation going in Discord, I will invite you to go there next. I can't believe you'd want to talk about more physics, but maybe you do. If you're doing E&M as well, the E&M CRAM is starting like right now. So at least like go take a lap or something before you jump on. But it is here. We are here for you to continue if you're taking E&M. But otherwise, hop over to Discord, talk to each other. Know that we're here for you. Good luck tomorrow. I'm so excited, and let us know how it goes. Thank you all so much. Have a great rest of your night. Good luck.